Picture standing on a distant hill, staring up at a sky that is not our own. The star above you looks a lot like the sun, warm and golden, but a little older. The air smells different. The ground feels heavier beneath your feet. Somewhere beyond the horizon, maybe green forests breathe under a brighter sky, or oceans glimmer beneath soft clouds. This place might not be Earth, yet something in your chest whispers, home, almost. For most of human history, we've dreamed of other Earths, but they lived in myth and hope. Then we began to search, and the universe began to answer. We found strange worlds first, but one day, telescopes caught the tiny, perfect dimming of a sun-like star, 1,400 light-years away. That shadow belonged to Kepler-452B, a planet we dreamed before we found it. Long before cities built walls of light that drowned the stars, the sky was a vast ocean of fire, and each point of light felt like a mystery with its own story. People stared upward and wondered if somewhere, on a world they could not see, someone else stared back. Humans imagined other Earths long before they understood what a planet truly was. In old villages and desert camps, in mountain monasteries and fishing boats under moonlight, people shared stories of lands beyond the sky. Some believed the gods lived there. Some imagined other people living under different suns. Some feared the heavens, while others felt a strange comfort in thinking our world was not the only one. Ancient Greek philosophers wondered if stars were distant suns. They suggested that other worlds might circle them the way our world circles the sun. They did not have telescopes or space probes, just logic and curiosity. It was a bold idea, almost rebellious at the time, because many people believed the Earth was the center of everything. To imagine other Earths was to stretch the human mind farther than anyone had tried before. It was like trying to imagine the ocean before ever seeing a river. Religious stories, too, carried hints of this dream. Some beliefs held that the universe was too grand for only one home for living beings. Others spoke about angels or other realms which still touched the same thought. That reality might be bigger than we see. Even when these ideas were not meant to describe physical planets, they kept alive the sense that existence stretches beyond the ground beneath our feet. Literature often reached for this dream in ways science could not yet do. Writers imagined travelers sailing beyond Earth to other worlds. They pictured strange lands, new skies, and unfamiliar life. In stories, characters stood on alien soil centuries before real humans ever left the atmosphere. These tales let the human mind explore what was not yet possible. They made the idea of other planets feel close, almost familiar, even when science had no proof. Philosophical thinkers argued that nature rarely makes only one example of anything. If there is one world that carries life, why would there not be others? To them, a universe with only a single living planet felt wasteful and lonely. They believed that nature, or a divine hand, or some deep logic of existence would repeat success. It was a simple idea, but powerful. It said we might not be a miracle. Instead, we might be part of something larger and shared. All these threads, across time and cultures, formed a soft foundation beneath modern science. The search for other Earths did not begin in a lab. It began around fires, under stars, in whispered questions from people who wondered who or what might exist somewhere else. When telescopes finally began to sweep the sky, they were guided as much by this old dream as by mathematics and glass lenses. It was curiosity shaped by generations of wondering. Each time we lifted our eyes to a telescope, we were also lifting the hope of countless ancestors who never saw a single planet, but still imagined them. When astronomers finally proved that planets orbit other stars, the world felt a shift. In a strange way, many people felt like the science was simply catching up to something we already suspected deep inside. But knowing other planets exist was only the first step. What truly touched our hearts was when we found one that looked like ours, a world with the right size, the right warmth, the right chance to hold oceans and air, a place that felt like a mirror in the dark. Finding such a planet touches that old dream and brings it into the light. When we see a world that could host life, even if it is far away and unreachable for now, we feel less alone. It does not answer every question. It does not give us aliens or cities or voices calling across the stars. But it gives us something that humans have sought since they first traced patterns in the sky. Proof that Earth might not be the only cradle of life. For most of human history, we thought we were the center of everything. Then we learned we were one planet among many. Then we learned our star was one among billions. And now we are learning that worlds like ours might not be unique. Each step carries both comfort and humility. We shrink, yet we grow. We become smaller in the universe, yet larger in our thinking. It is a strange kind of beauty, like standing on the edge of the ocean and feeling tiny, but thrilled by the size of it all. We build better telescopes, launch spacecraft and analyze faint signals from far stars, searching for hints of water, atmosphere and chemistry that could support life. But beneath the technology, the spirit remains ancient. Every discovery is still tied to those first skywatchers who did not have data but had imagination. How humanity began searching for another Earth. For a long time, scientists could only study the movement of visible planets in our own solar system. They watched Mars, Jupiter and Saturn through small telescopes and learned how gravity shaped orbits. They mapped the sky and measured star positions with growing skill, but none of it showed a planet around another star. Even the best equipment could not pick out something so faint. The universe looked empty between the stars, and some began to wonder if the dream of other Earths would always stay a dream. Still, the search never stopped. As technology grew during the industrial and scientific revolutions, tools improved. Telescopes became sharper and larger. Cameras replaced the human eye in astronomy, allowing long exposures that captured faint light. Computers entered the picture and began helping scientists sort through data, looking for tiny patterns the human eye might miss. The hunt for planets became a quiet, steady goal in the background of astronomy. By the middle of the 20th century, a shift began. The same era that brought rockets, satellites, and the first astronauts also sparked new hope in the hunt for other worlds. Scientists realized that if they could not see planets directly, maybe they could detect them indirectly. Stars pull on planets, but planets also pull on stars. Even a giant star can wobble ever so slightly if something heavy orbits it. This wobble was too small to notice for most of history, but with new instruments, astronomers started trying to measure it. Many believed the task was hopeless. Detecting a planet by its tug on a star required precision almost beyond human engineering at the time. But science often begins with stubborn belief. Researchers kept building better tools, refining their instruments and trying again. They created devices that could split light into pieces and measure tiny shifts in a star's color. When a star moved toward us, its light stretched a little. When it moved away, it shifted the other way. This effect, called Doppler shift, became the first reliable way to search for worlds we could not see. Even with this method, progress was slow. The first confirmed exoplanet around a normal star was not found until 1995. It was not like Earth. It was a gas giant orbiting very close to its star. But it proved planets were out there. Suddenly, the dream rushed into the real world. If one planet existed, then many more must too. It was as if a door had opened in the sky. Once technology caught up to the imagination, the search accelerated. Astronomers built instruments designed specifically for planet hunting. Telescopes on mountaintops scanned starlight night after night. Computers sorted through tiny wobbles and shifts, looking for patterns that betrayed a planet's pull. The first discoveries mostly found large planets, gas giants like Jupiter, because they created bigger wobbles. But the goal was clear: find an Earth-sized world in the right distance from its star, a place warm enough for liquid water and maybe life. A second method soon joined the hunt, the transit method. Instead of watching a star move, scientists watched stars dim. If a planet crossed in front of its star from our point of view, it blocked a tiny bit of light. The dip was small, often just a fraction of a percent, but it could be measured with the right instruments. This method opened a new chapter. Instead of guessing, astronomers could see when something passed in front of a star and learn its size by how much light it blocked. A star could blink, and that blink could reveal a world. To use this method well, scientists needed telescopes in space above Earth's atmosphere where air and clouds would not interfere. This led to missions like Kepler. Launched by NASA in 2009, Kepler did not roam the solar system like a Voyager. It did not turn to look at galaxies or nebulae or comets. It looked at one patch of sky, roughly the size of a fist held at arm's length, and stared without blinking. In that patch were more than 100,000 stars. Kepler's mission was simple. Look for tiny dips in starlight and see if they repeat. A dip could mean something moved across the star. A repeat dip at a steady interval could mean a planet circling again and again, like clockwork. The transit method was already proving powerful on Earth. But from space, without air shaking the telescope's view, Kepler could measure brightness changes smaller than a fraction of a percent. It could see a star dim by the tiniest amount. And soon enough, Kepler found planets. Hundreds, then thousands. The universe shifted again. Planets were not rare, they were everywhere. Most were not like Earth. Some were scorched worlds hugging their stars. Others were icy giants drifting in cold darkness. But a few stood out, sitting in their star's habitable zone, the region where temperatures might allow oceans. Each one felt like a new whisper from the old dream. Earth was not alone in its ability to host life, at least not in theory. With every discovery, tools improved. Scientists began using powerful ground telescopes and new space instruments to measure atmospheres. By watching starlight pass through a planet's thin air, they could look for signs of chemicals like oxygen, methane, or water vapor. They tracked how fast planets orbited, how heavy they were, and what they were made of. Each step brought us closer to understanding not just where planets are, but what they are like. Behind these discoveries were years of quiet effort. Engineers built sensors more sensitive than anything before. Astronomers developed software to sift through oceans of data. Mathematicians wrote models to predict how a planet tugged or dimmed or shifted light. It was not loud or dramatic work. It was patient, steady, and full of moments where things failed before they succeeded. But each small advance moved us closer to the truth. In time, other missions joined the search. Space telescopes and observatories spread across continents and orbits. Some scanned nearby stars, hoping to find worlds close enough for detailed study. Others looked far across the galaxy, hoping to map the full spread of planets in the Milky Way. Scientists even began dreaming of missions that could take pictures of distant planets, showing oceans, clouds, or continents, if they exist. What once was pure imagination now stands on the edge of engineering plans and budget proposals. Even today, we cannot see most exoplanets directly. They remain tiny specks lost in the glare of their stars. But we can feel their presence in the data, like footsteps in the snow. Each signal is a promise. Each measurement is a thread we pull to reveal a larger shape. The universe has started to answer the question that humans asked long before they had the tools to listen. The Kepler mission, Eyes on a Sea of Stars. The choice of where Kepler pointed was not random. It stared into a region of the Milky Way rich with stars, but not crowded with bright, messy objects that could confuse its detectors. This zone sits between the constellations Cygnus and Lyra. To a casual skywatcher, these stars blend into the background, but to Kepler, they were a treasure field. Most of the stars it watched were far away, hundreds or even thousands of light years from Earth. We could not dream of visiting them. Yet they served our purpose perfectly, a huge sample to see if planets were rare or common. Many people outside astronomy did not expect a revolution. A space telescope staring at tiny changes in starlight sounded delicate and quiet compared to rockets, rovers, or the grand missions of the past. But Kepler was a silent breaker of boundaries. It was like placing a microphone at the edge of the universe and hearing whispers that had always been there but never caught before. Each dip in brightness might be a world passing in front of its sun. Some dips were large, caused by big planets. Some were barely visible, possible signs of small, rocky worlds that could be cousins to Earth. The telescope worked by taking constant measurements. Every 30 minutes, it recorded the brightness of its stars. Day after day, month after month, year after year, it collected light and saved it. The data piled up, forming timelines of star behavior. From these lines, scientists could mark dips, measure patterns, and see rhythms. At first, the discoveries came slowly. Learning to read Kepler's data took patience. A dip could be many things: a planet, a star spot, a binary companion, even a cosmic glitch. Teams of researchers built models, checked signals, and filtered out noise. They learned how to tell true planets from false hints. As they did, Kepler began speaking more clearly. One discovery became 10, 10 became dozens, dozens became hundreds. Before long, scientists were announcing new planetary candidates by the hundreds and then by the thousands. We found hot worlds that orbited their stars in days. We found super-Earths that seemed too big to be rocky and too small to be gas giants. We found planets in places where many models had said they should not exist. And most thrilling of all, we found worlds in habitable zones, where temperatures might allow oceans, where life might form under gentle sunlight. None of these planets were proven to hold life, but they made something clear. Earth was not a lone miracle. The universe builds worlds by the handful, the dozens, the thousands, maybe more. Before it launched, we did not know how common planets were. Some thought they might be unusual, but Kepler's data showed the opposite. Planets are common. Stars and planets go together the way soil and seeds do on Earth. Where one exists, the other tends to follow. And if planets are everywhere, life might not be rare either. One of the most surprising results was discovering how many planets are small. Gas giants are dramatic, easy to imagine, and easy to spot with older tools. But Kepler showed us that the galaxy prefers to build worlds closer in size to Earth or a little larger. These super-Earths, though unfamiliar to us, are among the most common planets in the cosmos. And while we cannot walk on them or test their air yet, knowing they exist opens new questions and possibilities. What if Earth is not the typical kind of planet where life forms? What if super-Earths are the true homes of biology in the universe? With each new discovery, the mission became a turning point in human history. Astronomers around the world dug into its massive archive of light curves and signals. Students trained on its data. Entire careers grew from understanding what Kepler had seen. The mission changed textbooks, models, and expectations. It made planet hunting a major branch of science instead of a fringe effort. And even after its steering wheels failed and its original mission ended, Kepler kept watching in a more limited mode, determined to keep searching until the last possible moment. It did not want to look away from that field of stars until it had given everything it could. When its fuel finally ran out in 2018, Kepler shut its eyes at last. But its legacy did not fade. Its data still lives, still studied, still surprising us. There are worlds hidden in its records that scientists are only now uncovering. It left behind not just catalogues and charts, but a new way of thinking about our place in the cosmos. Before Kepler, the universe felt big but mostly empty. After Kepler, it feels full, alive with potential worlds, each one holding its own story. The day we met Kepler, 452B, in 2015, after years of watching the stars and sorting through mountains of data, NASA announced the confirmation of a planet that made astronomers lean forward in their chairs. Kepler-452B. Its name sounded strange and technical, like a code rather than a home. Yet beneath that dry string of letters and numbers was something human, a world a little larger than Earth, circling a star so much like our Sun that astronomers called it an older cousin. It sat in the zone where water could remain liquid, where life, at least in theory, could take root. It was not the first exoplanet. It was not the 100th. but it was the first that felt like it might belong in the same family as Earth. The journey to this moment did not begin with fanfare. It began quietly, inside data streams gathered by the Kepler telescope. Every dip in brightness from every monitored star had to be checked and tested. Most dips were noise or caused by stars that dimmed naturally, or by systems where two stars orbited each other and fooled the instruments. Researchers had to test again and again, like detectives checking footprints in soft soil, trying to see if they were made by a visitor or just the wind. Kepler-452B took time to reveal itself. Its star, now called Kepler-452, is slightly older and brighter than the Sun. A planet orbiting at just the right distance would take roughly a year to complete a circle. That meant Kepler could only see a dip once per orbit. To be sure the signal was real, scientists needed multiple dips, spaced evenly across years, and even then they needed to check and model and rule out every other explanation. They wanted to be careful, because this discovery was different. If they called it wrong, they would be stepping on the dream with their own weight. When NASA scientists were finally confident, they prepared the announcement. Inside the science community, word began to spread in quiet waves before the public knew. There was excitement, but also caution. Astronomers are trained to hold emotion at arm's length when the numbers arrive. They know nature can trick even the most careful observer. Yet in the corners of labs and behind computer screens, smiles began to appear. Then the announcement came. NASA held a press briefing and the world listened. The language was measured. The presenters explained what they had found. A planet 60% bigger than Earth, likely rocky, possibly with clouds and oceans if conditions were right. Its star was a slightly older shade of gold. The planet sat in the zone where temperatures could support water. The team did not call it Earth-like in a dramatic way. They did not make bold promises. Instead, they spoke like mountain climbers who had reached a high ridge and could see something that looked like the peak in the distance. The public heard the message with hearts rather than data sheets. Headlines called it Earth's cousin, Earth 2.0, a second Earth. Social media flashed with images of imagined alien forests and oceans. People dreamed freely, filling gaps with hope. It was as if a door had cracked open and we could feel a breeze from another world, even if we still could not see inside. Inside NASA and scientific institutes, the mood stayed grounded. Researchers used careful terms. They spoke of potential habitability rather than life. They reminded everyone that the planet was far away, too far for our current probes. It would take tens of thousands of years to reach with today's spacecraft. But even with caution, they knew what the discovery meant. Before Kepler-452b, planets in habitable zones had been found, but around stars very different from the Sun. Many were around dim red dwarfs, where flares could strip worlds of air. Others were distant gas worlds, where life as we know it seemed unlikely. Kepler-452b was different because it fit into a shape humans recognized. An Earth-sized world in the gentle glow of a sun-like star. Not too close. Not too far. There had been other finds that sparked talk, but this one landed quietly and firmly, like a footstep on solid ground after years of walking through fog. Scientists across the world reacted with a mix of excitement and relief. For decades, models predicted that Earth-like planets should exist. This was a sign that the predictions were not just hopeful math. The universe had followed the same pattern twice, and if twice, then likely many times. Some researchers said it was the most important exoplanet discovery yet, because it suggested that our solar system might not be a once-and-forever story. There was also a soft sadness in the reaction. Kepler-452b is more than 1,000 light-years away. Even the signals we receive today left that system before humans built the first stone walls. The planet could be beautiful or barren, or home to life that rose and fell before our species walked upright. Its oceans could be blue and deep, or its land could be dry under an aging sun. We cannot know yet. The distance is a barrier as real as a wall, but knowing it exists changes the map in our minds. After the announcement, telescopes and missions did not suddenly shift toward Kepler-452b. We could not zoom in, we could not send a probe. The best we could do was admire the data and hope that future tools might study its air or climate. Yet even without pictures or samples, the planet settled into the public imagination. School children heard about it. Artists painted it. Thinkers compared its star, older than ours, and wondered if life there might be ancient, wise, or long gone. Writers wove stories around it. For months, the name floated through news stories and conversations, like a tune stuck in the world's mind. Inside science, the discovery acted as fuel. It pushed researchers to build better missions. It justified new telescope plans and shaped the goals of future observatories. If one Earth cousin existed in one small patch of sky, how many others waited? Kepler had looked at only a tiny slice of the galaxy. That meant Kepler-452b was likely not rare. It might be one grain of sand on an endless beach. The day we met Kepler-452b did not bring proof of another living world, but it told us that the universe builds Earth-like planets around sun-like stars, and that at least one sits in the gentle warmth where rivers could run and air could breathe. We had waited long. We could wait longer, but waiting no longer meant hoping without reason. Now we had a place to point to, a real world marked on the star map of our minds. Early exoplanet breakthroughs. When we look at the early years of exoplanet discovery, it is tempting to imagine a smooth and steady path. But the truth is far stranger. The first solid discovery arrived in 1992, and it shocked nearly everyone. It did not orbit a star like the Sun. It did not even orbit a living star. It circled a pulsar, which is the dense, fast-spinning remnant left after a star explodes in a supernova. A pulsar is not gentle. It blasts beams of radiation like a spinning lighthouse in space, pulsing again and again with perfect rhythm. Around one such object, named PSRB 1257 plus 12, scientists found not one but two planets. Soon after, they found a third. These worlds were circling a dead star. The early dreamers had hoped for a planet like Earth, orbiting a quiet star like our Sun, with seasons and stable warmth. Instead, the first confirmed exoplanets were survivors of cosmic destruction, scorched by the memory of an explosion and bathed in harsh radiation. Their existence rewrote the rules. If planets could form or somehow remain around something so violent, then nature's creativity in building worlds was far greater than anyone had guessed. These pulsar planets showed that the universe did not play by human expectations. But the surprises did not stop there. In 1995, another breakthrough came, this time around a star more like the Sun. The planet was named 51 Pegasi b. At first, many scientists did not believe it. They thought the evidence must be flawed. The problem was not that it was small and rocky like Earth. The problem was the opposite. This planet was huge, and it orbited so close to its star that it completed one full year in about 4 Earth days. Imagine a giant world skimming its sun so closely that its atmosphere boiled and storms raged endlessly. Before this, scientists thought big gas giants should form far from their stars, just like Jupiter and Saturn in our solar system. Having one hug, its star broke the ideas many astronomers trusted. It meant that the early models were incomplete. Nature was doing something very different from what we had assumed. Planets could migrate. They could shift from far orbits to near ones. They could form in strange places or move into them. The old picture of neat planetary systems like ours had to be thrown away. Instead of finding safe, mild worlds with oceans and stable climates, astronomers were finding wild objects that looked more like nightmares. But each surprise also taught something important. It showed that planets come in many forms, and that our solar system was only one example, not the blueprint for the universe. The early discoveries also showed that we needed new methods and sharper tools. Hot Jupiters were easier to detect because their size and close orbits made them tug strongly on their stars or block noticeable amounts of starlight, when they passed in front. In other words, we found them not because they were common everywhere, but because they were easiest to spot with the technology of the time. Earth-sized planets, small and faint, would need patience and better instruments to uncover. The universe was not hiding them out of cruelty. They were simply quieter than the giants we first stumbled upon. As the 1990s turned into the early 2000s, discovery after discovery arrived, and nearly each one challenged what scientists thought they knew. There were planets twisted into stretched orbits that looked more like comets than worlds. There were gas giants circling twin stars. There were planets that seemed to skim so close to their suns that their atmospheres might be blown away. Worlds of all shapes and orbits appeared, painting a picture far stranger and richer than human imagination had dared to draw. Each find forced scientists to rewrite theories about how planets form. Early models had suggested calm and orderly systems like ours, with small rocky planets near the Sun and gas giants farther out. But nature showed chaos was possible. Giant worlds could shift inward. Stars could host planets in tight chains or thrown out paths. There were even signs that some systems might have lost worlds long ago, thrown into space or swallowed by their stars. For the first time, astronomers began to see planetary systems not as neat families, but as living, evolving structures shaped by gravity, collisions, and time. Planet formation turned out to be more like weather than architecture. It followed patterns, yes, but those patterns could twist, crash, and branch in countless ways. The early years of exoplanet study were like wandering into a jungle we thought we knew, only to find creatures unlike anything in our books. If the universe could surprise us so much, then finding another Earth would not happen by luck or speed. It would take time. We had to learn how to listen more carefully to starlight. We had to build tools that could sense tiny hints instead of loud signals. We had to study thousands of worlds that were not like ours to understand the patterns that might lead to one that was. By the late 2000s, scientists had confirmed hundreds of exoplanets, but still no true twin of Earth. Many people outside the science world did not realize how big a task it was. The excitement of early discoveries had created a hunger for a world like ours. Yet each new find reminded researchers to stay humble. The universe was bigger and stranger than we thought, and our place in it could not be revealed quickly. These early discoveries were necessary steps. They trained us to think beyond our own solar system. They forced us to accept that we had only seen one version of what planets could be. And they prepared us for the moment when technology would finally become sharp enough to find worlds closer to the dream humans had carried for centuries. When Kepler-452B finally appeared in the data, it did not arrive by accident. It appeared after years spent learning from planets that were nothing like Earth. Every odd world, every hot Jupiter, every planet around dying stars paved the way toward the ones that felt familiar. They were the stepping stones across a cosmic river, each one strange but each one needed. Without them, the path would have remained hidden. And so, the first chapter of exoplanet discovery was less about finding another Earth and more about learning how vast and unpredictable planetary nature can be. Transit light dips and stellar heartbeats. The transit method begins with light. If a dip in light returns after a fixed time, again and again, then a pattern begins to speak. Each dip marks another lap around its star. By timing the dips, scientists learn the planet's orbital period. By measuring the depth of the dip, they estimate the size of the planet. With careful analysis, the shape of the dip can reveal even more. It can show whether the planet has a clean round path, or whether other planets tug at it and stretch its orbit. Sometimes it can even hint at clouds or rings. Yet the universe does not make this easy. Stars are not perfect bulbs. They tremble, they flicker, they swell and shrink slightly in temperature. They have storms. They have spots that rotate in and out of view. Each of these changes can look like a fake transit, so astronomers must filter and compare, checking whether a dimming event looks like a true shadow or just a trick of nature. If the star pulses in a steady beat, it can hide a transit inside that beat. If the telescope shakes even a little, it can produce false dips. Thousands of stars, thousands of dips, but only some of them are real. This is why a possible transit is only the first hint. To be certain, scientists often use the radial velocity method for a second look. The star's wobble isn't extreme. Sometimes it's only a few meters per second. A planet like Jupiter makes a strong wobble. A planet like Earth barely tugs at all. So when astronomers try to measure the wobble of a sun-like star caused by an Earth-size world, they deal with motion that could be smaller than the speed of a slow walk. It is like trying to feel a feather landing on your hand while standing in the wind. To measure these tiny shifts, telescopes must be stable to the point of perfection. The sensors must not drift. The temperature inside the detectors must not change. Even the slightest shift in equipment could look like a false signal. Scientists build instruments cooled and sealed, anchored to vaults deep in observatories, all so that a star's tiny wobble does not get lost. They watch the star again and again, taking thousands of data points. With each observation, they try to see if the light moves in a steady rhythm. A rhythm means a planet. If the rhythm repeats every 365 days, it could mean an Earth-like year. But stars make their own music. They shake and ring like giant vibrating spheres. Convection inside their layers causes ripples. Sound waves bounce within them. These stellar heartbeats can mimic the wobble caused by a planet. So astronomers must learn to separate the music of the star from the tug of a planet. They model the star's inner noise. They observe for months, sometimes years. The planet's rhythm slowly stands out, steady and patient, like a soft drum beneath the fluttering surface. A transit by itself could be fooled by star spots or stray objects. A radial velocity signal can be confused by star activity. But when both appear together, when a dip in light and a wobble in motion match in timing and strength, the signal becomes solid. One method says, something passed in front. The other says, something is tugging here. Together, they tell a full story: size, orbit, and often mass. From mass and size, scientists can guess whether the planet is rocky or gaseous. With more data, they can estimate surface gravity and perhaps temperature range. This careful process is why new planets are not announced lightly. Each one is the product of countless hours of watching, testing, and retesting. Whole teams check every step. Computer programs search for errors. Peer review challenges the findings. When a planet is confirmed, it carries weight. It is not a rumor, but a quiet fact won through patience. And still, much remains unseen. A transit only happens if the orbit lines up perfectly between star and observer. Most planets never pass in front from our view. The wobble method works best for stars close to us. Farther ones whisper too softly. So even with these tools, we see only a small slice of all the planets that must be out there. For every world we find, many others remain hidden, waiting for future eyes, future instruments, and future patience. A planet in the Goldilocks zone. When scientists talk about a world that could host life, one idea rises again and again: distance. Not how far the planet is from us, but how far it sits from its own star. This distance decides how warm the surface might be, how much energy the planet receives, and whether water, the simple ingredient that supports life on Earth, could flow or pool or fall as rain. If a planet is too close to its star, heat blasts the surface, water boils or never gathers at all, and the world becomes a searing desert stripped of oceans. If it is too far, cold locks everything in ice, freezing lakes, freezing skies, and perhaps freezing any chance for chemistry to bloom. Somewhere between those extremes lies a thin, gentle band called the habitable zone. Many people call it the Goldilocks zone, inspired by the old story where a place must be not too hot, not too cold, but just right. It is a simple idea. Stars release energy not just as warmth, but as a wide range of radiation. A planet must be close enough to gather enough energy to keep water from turning to ice, yet far enough that it does not lose all its atmosphere or ocean to heat. This balance depends on the brightness and temperature of the star. A small cool star needs planets to sit close in tight orbits to stay warm. A large bright star needs planets to orbit farther out. So the zone shifts with every star type, a moving ring of possibility. For our Sun, this zone stretches from roughly where Venus orbits to somewhere around Mars. Earth sits right inside it, not at the center, but in a comfortable place where oceans can exist and stay liquid over long ages. That placement shapes nearly everything we know. Our clouds form from water, our rivers carve land, our plants drink, our bodies rely on liquid water to move chemicals and energy. Without this simple condition, life as we understand it might never start. We do not know if alien life needs water exactly the way we do, but water is a strong guess. It dissolves minerals, carries nutrients, and helps complex chemistry happen. So when scientists search for life, they begin with this question: could water stay liquid there? That question brings us back to distance. Imagine a fireplace in a cold cabin. Sit too close and the heat burns your face. Sit too far and you shiver. You must find the distance where warmth reaches you without harming you. Stars act like cosmic fireplaces, each with different flames. Red dwarf stars burn low and long. Yellow stars, like our Sun, burn steady and bright. Blue stars blaze fiercely and live fast. Because each star type has a different strength, each habitable zone sits in its own unique place. When we search among the stars, we are really searching along these invisible rings, hoping to find a small world sitting in the quiet middle ground. But the zone is not a perfect promise. Planets shift in their orbits. Some wobble closer and farther over long cycles. Some have thick atmospheres that trap heat like a blanket. Others have thin skies that let warmth escape. A planet in the correct zone could still be barren if it lacks the right air, or if storms sweep away its water. At the same time, a planet outside the zone could still be friendly to life if warmth comes from inside, like the moon Europa around Jupiter or Enceladus around Saturn, where ice hides oceans heated from below. Yet even with these exceptions, the habitable zone remains our main guide. It is the first place we look, the first circle we draw around each star when we begin our search. Kepler-452B sits in this circle around its star, which is very much like our Sun. Not colder, not wildly hotter, but familiar. It was positioned in a way that reminded scientists of home. Each number from that discovery spoke quietly but clearly. Sunlight that could feel like ours, heat that could allow lakes and rain, conditions that might let chemistry grow into biology. We cannot see its oceans. We do not know if it has any at all. But it sits in the zone where water could exist, and that is enough to hold the imagination. To measure a planet's distance from its star, scientists use the orbit timing from transits or the wobble from radial velocity signals. They calculate how much energy the planet receives. They check the star's brightness and temperature. Then they map the planet's orbit inside or outside the known habitable band. Every number carries uncertain edges, small measurement errors, variations in star brightness, the unknown thickness of a planet's air. Even so, the process gives a strong starting point. The zone is an invitation to study further. In the early days of exoplanet research, many discovered planets sat far outside this zone. Finding planets inside the Goldilocks zone was rare and thrilling. When Kepler-452b appeared in data, its orbit placed it in that narrow band. Not too close, not too far. A round path in a space where warmth could settle gently on a surface. That fact alone meant this world could sit in a calm place, warmed by familiar light. The habitable zone is not a promise of green valleys or deep oceans, but it is the doorway through which such possibilities begin. Many worlds will sit in this zone and still be unkind to life. Some may be dry, some may be covered in thick, choking skies, but among many, one may hold the right mix. And to find that one, we begin with this simple measure: distance from a star and the quiet question that follows. Could water move here? Could rain fall here? Could something living breathe here? Comparing sizes, a super-Earth with familiar traits. The term super-Earth sounds like something from a comic book, a world like ours but stronger, Bigger bones, a little more muscle. Kepler-452B fit that idea, sitting just beyond Earth's size, not huge like a gas giant, but large enough to make scientists pause. It was like Earth, only stretched slightly, as if the universe had pressed gently on the edges and added a little extra weight. And that extra weight matters. In space, even small differences echo far and wide. Size shapes gravity, and gravity shapes everything that follows. Imagine walking there. Each step would feel heavier, like carrying a pack you did not ask for. Not so heavy that you would fall to your knees, but heavy enough to remind you with each breath that this was not home. Your muscles would work harder without asking your permission. Your bones would feel that gentle pull, tugging you closer to the ground. A stronger hug from the planet beneath you. If you carried a stone in your hand, it would seem to press back, almost stubborn. Even the air might feel slightly thicker if the world held a deeper blanket around itself. A bigger world can hold on to more gas, and that grip could change everything from wind to clouds to the way light softens in the evening sky. Think about mountains. On Earth, tall peaks punch toward the sky, their tips cold and sharp, but size can press mountains down. On a heavier world, even a mountain's ambition is limited. The planet's weight works like a sculptor with firm hands, pushing stone back toward the core. Peaks would rise, but not as boldly. They might look gentler, more worn, like old giants who bowed their heads over time. Valleys might feel deeper, because your body feels deeper in everything, pulled more firmly to the ground. A traveler there might sense the landscape differently, as if the land had a quiet strength, always leaning inward. Then think about oceans. Water listens to gravity too. A slightly heavier world might hold oceans in shapes we cannot fully comprehend. Waves could hit harder, coasts could feel tighter, water pressing down more strongly on every drop below it. If deep seas formed, their depths might be even more extreme, layers of water stacked under greater pressure. Life in such oceans, if it ever existed, might have needed strong bones or flexible bodies built to survive the squeeze. Even simple things like bubbles rising would behave differently, maybe slower, maybe smaller, shaped by that extra pull. The familiar dance of sea spray and surf might have a different rhythm. On Earth, air thins as you rise. We climb mountains and feel breath grow shorter, steps slower. On a heavier cousin world, that change might happen faster. A jog up a hillside could feel like a climb to a high peak at home. Clouds might build in layers that press tighter around the world. Storms could behave in new ways, carrying more weight, packed with thicker energy. Even a breeze might feel different, steadier or more powerful, shaped by a deeper atmosphere pressed closer to the surface. And yet nothing here is certain. No telescope has shown us these oceans or mountains or skies. We do not have pictures. We do not have samples. What we have is gravity, that quiet rule that guides all worlds, giving us clues. This planet may not match every guess. It could surprise us in ways we have not yet dreamed, but gravity does not lie. A bit more mass changes the story. A world becomes less forgiving. A leap becomes a strain. A climb becomes a test. Even the ground beneath your feet would tell the tale. Rock under pressure behaves differently. Crusts might be thicker or thinner depending on the heat moving inside. Volcanoes might rise, but their shapes and flows could differ. A heavier world might cool slower, holding warmth longer, pulling at magma chambers with stronger force. Lava could spread in wide sheets instead of rising high. Plate movement, if it existed there, could grind harder, shaping landscapes with deep scars or smooth plains, depending on how the world's inner engine behaved. Life, if it ever formed, would have followed these rules too. It would have grown under a stronger pull, shaped by that extra grip. Plants, if they grew, might be shorter, hugging the ground for support. Tall trees on Earth must fight gravity to stand. On a heavier world, the fight would be harder. Animals, if any ever roamed, might carry strong, thick limbs or squat bodies built to push against the constant pull. Lighter bones might snap. Thin frames might buckle. Nature always listens to physics first. For humans, if we ever stood there, time would teach us new habits. We would walk slower at first, then stronger as muscles rebuilt. Our hearts would learn a new rhythm, pushing blood under a slightly greater load. We would breathe deeper without thinking, training the body quietly. Even rest would feel different, as if the planet itself was always reminding us of our place in the balance of things. The ground would not harm us, but it would not let us forget it. A little extra size, a little extra pull, and suddenly wind, water, stone, and flesh all face new rules. It is a world that might feel both familiar and distant if we could ever stand upon it. A cousin you recognize in the eyes and smile, yet who carries a life shaped by another path. This is the quiet magic of scale. The universe does not need to make a world twice as large to make it alien. It only needs to nudge the dial. That is why scientists pay such close attention to numbers here. They know that living on a world like this or studying it means understanding how those tiny shifts ripple across everything a world can be. The surface may echo home, but gravity writes its own poetry. The host star, Kepler-452, and its solar-like nature. When we look for another Earth, we do not just look for a familiar planet. We look for a familiar fire in the sky. Kepler-452 fits that hope in a rare and comforting way. When scientists saw it, they saw something close to home. A star like our Sun carries a special promise. It burns steady. It shines in a way that does not wildly shift from bright to dim. Life needs calm. It needs patience from the sky above it. Stars that flicker with fierce storms or blast their planets with harsh radiation make life fight too hard, too soon. But a star like Kepler-452 gives its light in a steady beat, long and soft across time. That stability is the quiet foundation every living thing depends on. Think of our own Sun. It has been burning for billions of years without wild swings or deadly bursts that strip away our air. Its warmth stays within a range. Kepler-452 carries that same feeling in its glow. Its temperature is close to our Sun's. Its color is that soft golden white that nourishes worlds instead of scorching them. Stars like this are builders. They carve time into long chapters where evolution can work its miracles slowly, with care step after step. Yet Kepler-452 is older. On one hand, that means it has offered steady light for a long time. On the other hand, it may now shine a little stronger than it did in its youth. As stars grow older, they burn hydrogen in their cores and slowly become brighter. It is slow, gentle, almost unnoticeable in a human lifespan, but across deep time, it changes everything. On Earth, scientists say that one day this rising brightness will warm the planet so much that the oceans will begin to shrink and clouds will thin. Earth will not become a fireball overnight, but the warmth will creep up over millions of years until life as we know it cannot survive. Still, the fact that this star fits the mold of our Sun is a gift. It tells us that when we finally found a world close to what we imagine Earth-like to mean, it was not circling a strange, violent, or unknown kind of star. It was orbiting a quiet golden furnace like our own. Picture its light falling over a world year after year, age after age. Steady rays warming soil, feeding plants if they exist, glimmering across oceans if they were ever there. Sunrises with a familiar color, sunsets with that same warm tint we know. The idea alone feels almost like memory, even though no human eye has seen it. That is the power of a sun-like star. It sparks recognition in the mind, as if we already know something about that sky. Kepler-452 does not drown its world in rage or starve it. In this balance, there is a sense of peace. It reflects the idea that life might not need chaos to begin. It might rise in calm, learning slowly to breathe, swim, walk, or dream under a light that remains patient. A sun-like star also means a solar wind and magnetic behavior that we understand. We do not need to imagine a strange kind of energy wrapping around the planet. We know how our Sun behaves and why Earth can hold its atmosphere close. We can look at Kepler-452 and feel confident that the physics at work follow rules we have lived under all our lives. And that gives scientists a roadmap. It invites study, comparison, prediction. If we wish someday to see Kepler-452b directly, to witness its sky, its land, its sea, or its silence, understanding its star is our first step. The star is the stage, and the planet dances only where the light allows. The star tells us how much warmth flows outward, how much energy shapes wind and rain if those things exist. A life-friendly star does not guarantee life, but without it, life has no starting place. We started here at home, under a star gentle enough to let time do its work. People sometimes imagine alien worlds under purple skies or near twin suns, or circling tiny red stars that flicker in and out like nervous lanterns. These ideas are exciting, strange, and fun to picture. But a sun-like star is not the wild frontier. It is like a neighborhood house we have never visited, but somehow believe we understand. We do not know the landscape, the air, the lakes or mountains there. Yet the sky, we tell ourselves, might feel right. An older sun. How stellar age shapes a planet's fate. Picture Kepler-452b in its early days. Maybe waves rolled under a gentle sun. Maybe rain fell on forests or plains, if life found a foothold. If rivers carved their way through stone, they might have sparkled like ours. But with time, the star grew brighter and the world warmed. A planet does not scream when this happens. Instead, water evaporates little by little. Clouds gather higher in the sky, letting heat slip through more easily. Lakes and shallow seas might shrink. The edges of oceans might pull back. As water rises into the upper atmosphere, some of it breaks apart in sunlight. Hydrogen escapes into space. The world loses its water not just to drying, but to the very structure of chemistry. The atmosphere thins in its moisture, turning from a cradle into a blanket with holes. If plants ever grew there, they might struggle. If life once swam beneath waves or clung to rock, it might face a long decline. On Earth, we read our future in science papers and modeling software. On Kepler-452b, that story could be history now. A star's age gives us a sense of time deeper than human history, deeper than the rise of continents. It reminds us that worlds have lives. They are born, they flourish, and they change as their suns do. Kepler-452b might be a world in a later chapter. The idea does not darken the story, it enriches it. Instead of thinking only of beginnings, we face the truth that worlds have endings too. A habitable zone is not forever. Think of Earth again. One day it will warm the way Kepler-452b may be warming now. Future oceans here will thin the same way. Scientists believe Earth is already slowly heading down that path, though we have a long future ahead before the Sun's natural changes force major shifts. Earth's fate is written in its star as much as in its rocks or its climate system. In that sense, Kepler-452b becomes a mirror of tomorrow. If life ever began on Kepler-452b, it had more time than Earth has had so far. Consider how much Earth has done in 4 billion years. Simple cells became complex ones. Plants reached for the sky. Animals swam, walked, flew, sang. Brains woke and looked at stars. If Kepler-452b had a head start, imagine the stories that world could hold in its rocks. Imagine a planet not behind us, but ahead. We do not know whether life began there, but age opens the door wide for possibility. The world had time to experiment. It had time to fail, or time to flourish. Even if the planet is drying now, that does not erase its potential past. Dry world does not mean dead history. Mars was once wet. Venus may have been calm before it became harsh. Kepler-452b could share this pattern: bright youth, stable middle age, warming later years. We often think of alien life in terms of what might be present now, but life can leave fossils, chemical traces, scars in rock. A world that is drying today may have been bursting with possibility long ago. Instead of searching only for perfect twin worlds, we begin to see planets as travelers through time, each shaped by their star's long heartbeat. We look at Kepler-452 not only as a match to our Sun, but as a guide to our Sun's future. When our star grows old, when Earth begins to warm in the same unstoppable rhythm, the oceans will speak the same language. And one day, far beyond human eras, Earth will stand where Kepler Kepler-452b might stand now. Age does not make a star weak. It makes it powerful in a different way. It pushes warmth outward in a steady climb. It invites reflection rather than fear. Kepler-452 glows like a lantern carried farther into the night. It has watched more orbits, seen more seasons sweep across its world, and its light carries the lessons of time. Climate puzzles. Could Kepler-452b still have oceans? Some researchers propose that Kepler-452b could still carry oceans. In this view, the planet may have found a balance. Perhaps it formed with vast seas, deeper and wider than Earth's. Larger planets can sometimes store more water inside their crust and mantle, releasing it slowly over time. Maybe clouds gather over its oceans, building thick blankets that reflect sunlight and lock moisture in. On Earth, clouds can cool or warm depending on how they form. On a world with slightly higher gravity and slightly stronger pressure, the cloud behavior could be different, maybe better at protecting water. If this is true, Kepler-452b might be a world with long coastlines and slow tides. Its horizon lined with green or storm-grey skies. A world still breathing through rain. But there is another picture, and it is more lonely. A planet that started like Earth, rich with blue water, might reach a tipping point as its star brightens. Oceans warm, evaporation rises, air fills with vapor that traps more heat, and the cycle feeds itself like fire taking hold in dry grass. Over millions of years, oceans may shrink, glaciers retreat, and lakes fade into salt beds. The air could grow thick with steam before the water breaks apart and escapes into space. At first, there would be storms, huge and powerful, driven by rising heat. Then the storms would fade as the last water disappears. What remains is a dry world, cracked and silent, with winds that carried dust where rivers once ran. There is also a middle path. Kepler-452b could be in transition. Maybe it still has lakes and oceans, but they are shrinking and shallow. Life, if it ever began there, could be struggling on the edges of survival, holding on in deep caves, underground water pockets, or shaded polar regions. When we think about oceans, we often picture open blue water and bright coasts, but life does not care about beauty. It cares about shelter. If there are refugees of water on Kepler-452b, they might hide in places far harder to find from across the stars. To explore these questions, scientists run simulations. They adjust temperature, pressure, gas levels, and surface types. They build models where the planet has more carbon dioxide than Earth, and others where it has less. They test thick atmospheres like Venus and thin ones like Mars. And in some versions, water remains. In others, it vanishes early. The results do not point one way. This is why Kepler-452b remains a puzzle. The truth is locked inside data we cannot yet gather. We cannot sample its air. We cannot watch clouds form or tides rise. We stand far away, looking at a point of light, trying to imagine an entire world from a handful of numbers. If Kepler-452b still has water, then perhaps it once had even more. If it has lost water, then maybe it once looked like our planet in its brightest days, full of life and noise. There is a quiet sadness in that idea, but there is also hope. Because if water can last longer than expected on a warming planet far older than Earth, then life might persist longer than we imagined too. It means planets do not follow only one story. Some may dry out fast, others may fight long battles against heat and win. Here on Earth, our climate has swung between ice ages and warm periods, and each shift has changed life. Forests became deserts, grasslands stretched, oceans rose and fell. Kepler-452b could have lived through greater swings, with longer ages of growth and decay. Maybe it once had continents thick with forests or plains filled with alien plants. Or maybe it always had a harsher climate, where only simple life could survive, clinging to rock and shadow. Right now, our tools cannot yet cut through the silence of space to see its surface. But this mystery pushes us to build better telescopes, to learn more about stars and climates, to understand how fragile and precious a balanced world can be. In the story of Kepler-452b, water is the central thread. If it is still there, then so is the dream that life has found a way to continue, even under an older sun. If it is gone, then the planet stands as a quiet warning of what time and heat can do. What we know for sure about the planet. The most certain fact about Kepler-452b is its size. We know it is roughly 60% larger in diameter than Earth. This number is the result of watching the planet dim its star's light as it passes in front again and again. From that pattern, we know its size relative to the star. From the same transit method, we also know its orbit length. Kepler-452b takes about 385 days to circle its star. That is close to Earth's 365-day year, only about 3 weeks longer. This part matters because orbit controls seasons, sunlight and stability. A wildly fast orbit could mean intense temperature swings. A slow one might bring long winters and summers. Instead, we find something calm and familiar. The numbers do not tell us whether this world has seasons, but they tell us its year is close to ours, and that alone is striking across such a distance. The star itself, Kepler-452, also gives us solid ground. It is a G-type star, and its temperature and brightness are very close to what we see in our own sky. We know its age is likely greater than our Sun's, perhaps by 1.5 billion years. That estimate carries more uncertainty, but the general picture is solid. Kepler-452 is old enough to have raised planets long past their early storms and impacts, guiding them into mature climates. We also know Kepler-452b orbits in the habitable zone. This does not guarantee rain or rivers or a single wet drop, but it places the planet in the right neighborhood. Still, for all these firm pieces, there are places where our grip loosens. We do not know its mass with perfect certainty. The size tells us Kepler-452b is bigger than Earth, but size alone does not tell us weight. For now, we estimate that the planet is likely around 5 times more massive than Earth, but that number has room to move. The likely mass leads us to think the planet has strong gravity and that thought shapes ideas about mountains, oceans, and even air pressure. But without a direct measurement, there is always a curtain of doubt. We do not know what kind of atmosphere it has, if any. The telescope that first spotted Kepler-452b was good at catching shadows and passing patterns, but not at tasting air from across space. Our instruments could not pull in its chemical fingerprints or read gases floating above its surface. We do not know if clouds drift there or if sky exists at all. Without an atmosphere, even a planet in a perfect orbit can be dry and barren, like the moon sitting in the sun's light, yet lifeless. So the question of air remains open, waiting for future tools sharper and stronger than those used in its discovery. We also cannot see its surface. Right now, it could be covered in deep oceans, or wrapped in dense clouds, or broken by rocky plains and peaks. It might have continents, or none at all. It might hold ice in its shadows, or face scorching heat plains. The planet does not offer us a clear photo or a detailed map, only a soft pattern of dimming light that hints at its round shape. Everything about its surface, from mountains to seas to colors, remains hidden behind distance and technology limits. It is strange to think how much a world can hide when seen from so far away. A single pixel could hold mountains taller than Everest, oceans wider than the Pacific, or deserts older than any life on Earth. We know the star-planet distance as well. Kepler-452b orbits about 5% farther from its star than Earth does from the Sun. That distance, paired with the slight increase in starlight due to its star's age, puts it in a heating zone where climate matters deeply. This distance gives structure to models and equations. But again, models must bend around missing details like air composition and rotational speed. We also know how long we have observed it. Not long enough to see its full history, but long enough to be sure it exists and moves the way we think it does. 3 recorded transits helped confirm its presence, each one marking another step from suspicion to certainty. Astronomers have seen enough to trust that this is not a mistake in data or a temporary glitch. It is a real world, steady and persistent in its orbit, circling its star in silence. Kepler-452b sits between known and unknown, offering a steady heartbeat of data surrounded by a fog of mystery. What we have is enough to build questions, even if it is not yet enough to build answers. Odds of life, statistics, science, and cautious hope. Life. The single most loaded word in the universe. It carries both hope and restraint. When we talk about Kepler-452b, this tension sits in every sentence. The pull between what might be and what we can actually support with evidence. No wishful thinking, but no cold dismissal either. There is space in science for careful wonder. To talk about life here, we start with a question that feels simple but rarely is. What are the odds? How often does nature stitch chemistry into biology? How many times does a planet cross from rock and water into something that breathes, grows, and changes the world around it? We do not know the true number, but we can talk about the tools used to think about it, and why even those tools sit on shaky ground. One of the most famous tools is the Drake equation. It began as a thought aid, not a hard formula, but it has shaped how scientists talk about life in the universe ever since. It breaks the question into parts. How many stars form? How many have planets? How many planets are in the right zone for life? How often life starts? How often intelligence rises, and how long those societies last? Each part has its own unknowns, and each step is smaller and narrower than the one before it. For the first few steps, we are much stronger now than when the equation was created. We know stars are plentiful. We know planets are common. We know planets in habitable zones are not rare. Kepler-452b itself is proof of that point. Rocky worlds in friendly orbits are part of the cosmic blueprint, but after that, the bridge becomes foggy. We do not know how easily life begins. We only know it happened here, and it happened fairly fast once Earth cooled. That gives us reason to think life may not be rare. Nature did not stall for billions of years. It moved. It used oceans and sunlight and chemistry to build something that could copy itself and survive. Still, it happened here is not the same as it happens everywhere. That is where caution enters. A single example can mislead. A single story cannot write the whole book. Maybe Earth was lucky. Maybe Earth is normal. We cannot yet say. Then comes the next narrowing step. Given life, how often does it become complex? On Earth, life stayed simple for a very long time. Microbes ruled for most of history. Complex forms needed more oxygen, stable climates, and long, steady stretches without global destruction. It took almost 4 billion years for anything with limbs, eyes, or nervous systems to appear. So even if life begins often, complex life might be rarer. It requires time, calm conditions, and maybe the right accidents. Kepler-452b sits inside this puzzle. If it once had oceans, if it once had stable temperatures, if it held on to its air for billions of years, then it had the basic stage for biology. But time cuts both ways. A planet that stays warm and wet long enough may see life flourish. A planet that stays too long under a growing star may see life fade or vanish. Kepler-452b's age makes both ideas possible. We look at Earth's history and we see how many steps needed to line up. We also see that nature can do incredible things when given time. There is quiet strength in the idea that life is not magic, but physics and chemistry under the right conditions. And if that is true, then every Earth-like world is not just a random point, but a chance, a roll of the cosmic dice. Some rolls come up empty, some might come up full. When we say maybe life is rare, there is fear behind that. And when we say maybe life is common, there is hope. Both feelings must sit in the background, but neither can guide the science. The universe does not bend to our wishes. Instead, researchers look for signals, a thick atmosphere with oxygen, a mix of gases that cannot stay stable without living processes, ocean glint, seasonal patterns, strange colors, chemical fingerprints. All these would point not to fantasy, but to something real. But we cannot see those yet for Kepler. Kepler-452b. A world like this can teach us patience. We are not rushing toward answers, but working toward them step by step. Missions are planned that will one day read the air of distant planets. Instruments are being built that will make today's guesses tomorrow's measurements. When that time comes, planets like Kepler-452b will move from mystery to data. Until then, scientists run models and compare to Earth. They ask, if this planet began like ours, how would its path differ under an older star? How many billions of years could oceans last? Could life adapt to rising heat? Could it move underground or underwater? Could it develop ways to survive change? These questions are serious, not imaginary. They connect geology, biology, and time. The odds of life elsewhere echo back as lessons for here. We realize how narrow Earth's safe zone is. We understand how sunlight slowly shifts across ages. We see how fragile oceans can be and how rare stability is on cosmic scales. If Earth has life, it is not because the universe promised it. It is because Earth earned it through balance and luck and long calm stretches. Life anywhere depends on peace. No endless storms, no constant heat spikes, no repeated world-breaking impacts. Just long, steady days where chemistry can play slowly, the way it did here. Every new planet we find shapes the curve of probability. The first Earth-like world was a spark. The second was fuel. The 10th, 100th, 1000th will be a story about the universe itself, not just about us. For now, Kepler-452b serves to show that the universe might be filled with seeds. Not all seeds grow, but some might. And the only way to know is to keep looking, keep asking, and keep building the tools that let us turn guesses into knowledge. The journey to understand life beyond Earth is slow, but it is steady. And each world like this one brings us closer to the truth waiting out there. Whether we are alone in the long night, or whether the cosmos has neighbors we have not yet met. What life there might look like under an older sun. On Earth, plants learned to stretch leaves towards sunlight, then later learned to protect those leaves from too much of it. Some developed waxy coatings, dense pigments, or tiny hair-like surfaces to limit water loss. Others changed their shape, thickening their stems or folding their leaves at certain hours to avoid heat stress. These are strategies that already exist here, shaped by our own planet's warmer and harsher regions. If Kepler-452b has plant-like life, it would likely follow similar logic, only pushed further. Instead of wide leaves like rainforest plants, life there might lean towards narrow leaf structures built to sip sunlight instead of drink it. Big, wide surfaces waste water under a hot sky. Thin blades, tight coils, or thick fleshy leaves might work better. Think more desert cactus than jungle fern, even if the planet once had oceans. As the star brightens over billions of years, the land would reward forms that hold onto water and shield themselves from heat. Pigments could be different too. On Earth, chlorophyll is great for collecting light, but too much light can damage cells. Some of Earth's toughest plants use darker pigments or extra chemical shields to handle high sunlight. Algae in harsh environments develop deep red or brown colors to protect their energy systems. If Kepler-452b's plants exist, they could be darker than ours, with pigments tuned to a star that slowly turned brighter. Deep greens, rust reds, browns, even almost black leaves are not fantasy. They are solutions that biology has already tested on Earth. Evolution retools chemistry. If Kepler-452b once had oceans and is now losing them, life might have shifted strategies. Some forms might move underground, where soil holds moisture and temperature stays stable. Root-like structures could reach deep underground, not only for nutrients, but for safety. Some desert plants on Earth keep most of their living tissue below the surface, sending up only small photosynthetic parts when conditions allow. A world growing slowly hotter might push life towards similar strategies. Quiet survival instead of open growth. If the planet still has large bodies of water, those waters could tell another story. Oceans are good at holding heat, but they also protect life from strong sunlight, especially in deeper layers. On Earth, some organisms near surface waters use pigments to protect themselves from ultraviolet light. Deeper down, creatures live in dimmer blue-green light and rely on slower energy cycles. On Kepler-452b, life might move deeper as the surface warms. Floating mats of plant-like organisms might grow thicker, shielding lower layers from harsh rays. Coral-like structures could build shaded underwater pockets. The rules are simple. Shield, store, endure. If Kepler-452b once had a lot of water vapor rising into the air, clouds could play a major role in life's struggle. Thick clouds can trap heat, but can also block sunlight. Life might have to adapt to changing light patterns, learning to thrive in bursts instead of steady supply. Some plants on Earth store energy efficiently, so they can endure long dry periods between rain. Life on Kepler-452b might refine that even further. Work fast when conditions are right, sleep when they are not. Daily cycles, seasonal cycles, long-term climate cycles. Evolution works across all of them. There is also the question of oxygen. If life there follows a path like Earth, early organisms might have used simple chemistry before building an oxygen-rich atmosphere. But on a warming planet, oxygen might rise and fall with oceans and temperature. Organisms might become good at switching between metabolism types, depending on what chemicals are available. Some microbes on Earth can do this today, shifting energy pathways when conditions change. On a long-lived world, flexibility could be one of the most important traits. Life might also favor smaller sizes. Smaller bodies lose heat faster and use fewer resources. They also evolve faster, adapting to slow environmental shifts. Plants might stay low and tight to the ground. Animal-like creatures, if they exist, might be small, quick and able to hide easily. Not giant beasts walking in sunlight, but compact bodies surviving in shade and soil. Insects and small reptiles thrive in deserts better than large mammals. If Kepler-452b has not yet reached its dry years, if it still enjoys a stable climate, then life might be more familiar. Large forests could exist in cooler zones. Oceans might still support rich ecosystems. But even then, every organism would live with a quiet pressure, the sun getting older, the world slowly changing. Evolution works best when there is a push. And this star provides a push across billions of years. We are not painting a picture of alien gardens or strange dream creatures. We are following rules that life on Earth has already shown. Conserve water, protect from heat, adapt to light, move when needed, hide when needed, endure. Biology follows chemistry and pressure and need. The details on another world would differ, but the shape of survival might rhyme with what we know. One day, our world will warm in the same slow, steady way. Plants will adapt, oceans will shift, life will find new niches or fall back to old ones. Nature will push, and life will push back. In studying that distant world, we learn not just what might live there. We learn what life really means when time becomes the test. If there are organisms under that older sun, they are not fragile wonders. They are survivors shaped by patience and pressure. They would not be shaped by dreams, but by the quiet logic of evolution. Life that fits its world the way a seed fits soil. Life that bends, shifts, holds on, and endures. If forests grew there, colors, shapes, and strange evolution. If forests ever covered Kepler-452b, they would not look like ours. Every tree, every leaf, every root would be shaped by an older sun, a heavier pull of gravity, and a sky that may hold more water vapor, or maybe almost none at all. Kepler-452b is likely heavier than Earth, so its pull downward would be stronger. Tall trees here grow upward because they balance strength and energy. But on a world with more gravity, growing tall becomes harder. Trunks would need to be thicker for support. Branches might not stretch far before dipping down under their own weight. Forests there might be lower, denser, with canopies closer to the ground. Instead of towering pines or reaching redwoods, imagine sturdy, wide-based trunks that spread their weight like strong pillars. Roots would answer this gravity too. To hold steady in thicker soil and resist stronger pull, root systems might spread wider and dig deeper. Some could wrap around rocks like clenched hands. Others might form thick knots just below the surface, anchoring against wind and shifting ground. On Earth, plants trade height for deep roots in harsh lands. On Kepler-452B, that trade might become the default. A forest there could feel heavy, grounded, full of plants that cling to the world like they never want to let go. On Kepler-452B, leaves might take on purples or deep reds to manage heat and radiation. Some could shine with waxy coats to reflect excess light, giving them a silver or blue-green finish. Imagine walking under such a canopy. Instead of seeing bright emerald leaves fluttering in sunlight, you might see darker shades absorbing and guarding. Light would spill through in beams filtered by pigments tuned to a slightly harsher sky. It would feel less like a cheerful garden and more like a world quietly adjusting to a sun that gives and takes at the same time. Leaf shape would change too. Narrower blades, rolled tubes, thick fleshy pads, leaves that fold at midday or tilt away from the sun at its peak. Forests on Kepler-452b might pulse with slow rhythms, opening to the morning, resting at noon, working again in late afternoon. A daily breathing pattern written into the branches. Now imagine how these forests hold water. If rainfall is rare or seasonal, plants would become master keepers of moisture. Bark could thicken to trap water inside. Leaves might drip condensed moisture back toward thick bases, where roots pull every drop inward. Some plants might collect morning dew with tiny hairs, feeding themselves before the world heats up. Others could shape their trunks into natural funnels, guiding brief rains into deep root wells. Nothing wasted, every grain of water treasured. In cooler regions, or if the planet still enjoys broad oceans, forests might grow thicker and richer. Yet even then, the patterns would reflect age and gravity. Trees might still remain shorter, creating layered canopies instead of towering giants. Moss-like layers or thick undergrowth could thrive in the shade beneath strong, low branches. Instead of vines climbing toward the light, they might spread sideways, weaving through trunks like living nets. Gravity invites sideways growth as much as vertical rise. And if the atmosphere carries more water vapor, the world may have frequent mist or fog. In such places, leaves could evolve to drink water straight from the air. Here on Earth, cloud forests already do this. On Kepler-452b, that trick might be widespread, with trees shaped like funnels or cups that channel fog droplets to their roots. You could imagine forests where branches stretch like arms not toward the sun, but toward drifting moisture, catching clouds instead of rain. The floor beneath these trees would also be different. Thick fallen leaves might break down slowly in places with less oxygen movement or drier air. Instead of soft moss carpets, the ground could be layered with tough fibers, dry mats, or wax-coated leaves resistant to decay. Or if conditions remain wet, the soil might be heavy and dense, filled with tangled roots that do not rot easily in cooler, shaded zones. Seeds and reproduction would follow their own path. On a heavier world, seeds might not travel far by air. Many plants might rely on dropping seeds close to the parent, or using wind only in short bursts. Others might develop heavy fruits that crack and feed the soil before sprouting. Without needing to reach tall heights, life could focus more on spreading sideways and building strong local networks. A forest might feel like one continuous organism, not thousands of individuals, but a slow-moving colony of growth and renewal. Colors along the ground would also shift. If leaves above filter the light into softer hues, plants below might evolve pigments to use whatever colors slip through. On Earth, under-canopy plants often turn darker green. On Kepler-452b, they might become deep violet or almost black, tuned to rare wavelengths that pass between thick branches. The world below the canopy might glow in strange tones, like an underwater reef lit by changing sunlight. Over time, forests could migrate. As heat grows, life might move toward poles or higher ground. Some species could retreat underground, forming bulb-like structures that emerge only in cooler seasons. Landscapes could show patterns of retreat and return, not just growth and spread. Imagine vast ancient tree lines marking where forests once stood, now replaced by tougher low vegetation, adapted to newer heat. Yet through all of this, forests, there would still be forests. They would still breathe in light and turn it into life. They would still build soil, cycle nutrients, and hold the planet's story in their rings or layers. Familiar in shape, strange in detail. A reminder that life adjusts and worlds write their own language of survival. Walking through such a forest would feel like nature wearing a different face. A heavier hush, deeper shadows, richer pigments, stronger forms. Quiet forms built for endurance. Forests that grew not for beauty or speed, but for time. Forests shaped not by quick storms or young climate, but by the long glow of an aging sun. Gravity and biology, life on a heavier world, on a planet like Kepler-452B, where gravity is likely much stronger than on Earth, life would not simply copy our blueprints. It would sculpt different bodies, different movements, different ways to stand, breathe, and survive. To live there is to live in a constant embrace of weight, where every bone and branch learns discipline. Start with shape. On Earth, many life forms stretch upward. Trees reach for the sky. Animals lift long legs and necks. Even our own bodies stand upright, supported by bones and muscles that fight gravity every second. But increased gravity and height becomes a luxury. Energy cost rises. Blood must be pushed harder. Structures must be thicker. A tall form risks collapse, so evolution would likely favor shorter bodies. Animals could grow compact and strong, and every living thing would hold itself close to the ground, as if hugging the planet that pulls on it so firmly. Muscles would thicken, joint structures would be reinforced, bones dense and sturdy. Even soft tissues might grow with tighter patterns, fibers layered like braided rope. On a heavier world, life does not leap lightly. Every movement, even a simple step, demands more power. So creatures might move with controlled, efficient motions instead of speed or sudden bursts. Think of slow, strong strides, low stances, and bodies built like living anchors. Not sluggish but steady, not weak but purposeful. On Earth, some animals jump to escape danger or catch prey. On Kepler-452b, jumping might be rare. It could be dangerous, wasting energy or causing injury on landing. Running might shift to powerful trots or heavy bounding close to the ground. Wings, if they exist at all, would face harsh trade-offs. To fly in stronger gravity, wings must be large and muscles immense. That makes flight costly, not impossible, but precious. Flying life might be rare, light-boned but incredibly strong, gliding more than flapping, using wind and terrain to save effort. A cliff or strong updraft could be a lifeline. Where Earth has gazelles that leap and birds that flutter, a heavier world might have squat gliders, powerful climbers and runners with wide feet to grip firm ground. Many forms might favor 4 limbs or more to share weight. Even a creature like a simple insect might grow thicker legs and a lower stance. Every footstep becomes a negotiation with the planet. Now think about internal systems. Hearts would need greater strength to push blood against stronger pull. Lungs might flatten and spread, working with slower breaths that move more air per cycle. Blood vessels could thicken to resist pressure. Earth's tallest trees already fight gravity to move water upward. On Kepler-452b, nature might choose different strategies. Water storage in tissues, roots sprawling sideways into shallow layers, or vascular systems tuned to slow, steady flow rather than height. Defense against predators or competition shifts too. On Earth, speed and flight are common defenses, but on a heavier world, quick escape becomes costly. Instead, protection might come from armor-like structures. Thick skins, plates, shells, layered bark. Strength becomes more common than swiftness. You might see creatures that brace instead of flee, or plants with fibers that resist tearing, because herbivores cannot simply sprint away after a quick bite. Feeding behavior follows the same logic. Predators may rely less on fast chases and more on ambush, patience, and raw power. A hunter might crouch in dense brush, muscles coiled, waiting for a heavy-footed grazer to wander nearby. When it strikes, the action would be brief and decisive because long pursuits waste too much energy. Prey, in turn, might develop powerful necks to pull tough plants or broad jaws to grind hardy vegetation. Nothing flimsy survives when gravity punishes weakness. Even senses might adjust with environment. Stronger gravity can create thicker atmospheres if other factors align, meaning sound might travel differently and smells may linger close to the ground. Eyes might sit low, bodies crouched, noses near soil rich with chemical signals. Communication could shift toward vibrations or low-frequency calls that travel through dense ground cover and air. In harsh heat, life might slow at midday, just as desert creatures on Earth do, but even more so because motion costs so much. Dawn and dusk could become windows of activity, with long periods of rest in between. Trees and plants might open pores to take in gases during cooler times and close them tightly when heat rises, locking precious moisture inside. If oceans exist, gravity still writes its signature there. Water movements change, waves break harder, currents push with more force. Marine life may favor compact bodies and strong fins. Buoyancy helps, but rising to the surface takes effort. Deep-dwelling life might thrive, anchored in place, filtering nutrients or using slow methodical strokes to glide along. Floating plants may cling to surfaces or develop thick root-like anchors that grip submerged rocks. These are all echoes of what Earth already shows us in high-pressure environments: deserts, mountains, dense forests, and deep seas. Our planet holds previews of what another world might invent. We see squat alpine plants that hug soil to survive harsh wind. We see burrowing creatures that conserve water and energy. We see stocky mountain goats balancing weight and strength. Nature always answers physics with creativity. If intelligent life arose there, even without describing culture or tools, their bodies would tell the same story. Low centers of gravity, strong limbs, lungs, and hearts tuned for effort, movement grounded and firm, steps deliberate. A kind of quiet grace that comes from living in a world that insists every action has weight. Gravity shapes bones and branches, habits and habitats. It asks life to work harder, to stay close, to build strength instead of height, endurance instead of speed. On a world like Kepler-452B, biology would follow its lessons. Life would learn to move differently, breathe differently, and hold itself against the pull that never rests. The result would be a world built on resilience, where every living thing stands not despite weight, but because of how it learned to live with it. Imagining sky, weather, and seasons. On Kepler-452b. On Kepler-452b, the sky may feel familiar at first glance. Yet when you look closer, the atmosphere and distance make a sky that follows rules of nature but still feels new. The light would fall in a softer way, slightly warmer in tone, because the parent star is older and a bit brighter. That glow could give the sky a gentle golden tint during long afternoons, as if every day holds a quiet memory of late summer on Earth. The air itself might be thicker, the atmosphere deeper. A heavier world often holds more gas, unless its history stripped it away. If Kepler-452b kept its air, then the sky could take on a layered look. Instead of a crisp horizon, distant views may fade into haze more quickly as tiny particles scatter sunlight. The horizon may blur into a soft gradient, shifting from pale blue near the ground to a richer tone above. On clear days, the sky might seem deeper, the way oceans look darker where they drop suddenly into depth. Clouds on such a world would follow the same physics as here, but scale and texture could differ. With higher gravity, air rises with more effort, so clouds might form lower and thicker. A world like this could have broad, heavy cloud decks that stretch for great distances, like massive blankets of vapor rather than soft cotton shapes. These clouds may trap heat in the lower atmosphere, holding warmth long after sunset. At times they could grow tall and powerful, but their vertical height would be more limited than Earth's towering storm columns. Instead of huge thunderclouds that stab up into the sky, storms might spread wide, covering vast areas with dark, slow-moving systems. Rain would fall heavier and faster. Each drop would feel pulled down with more force, slamming into soil and rock with greater speed. Storms might sound different here, louder with rain that hits the ground like tiny stones. Wind patterns would also shift. With higher air pressure and gravity, wind could move thick masses of air close to the surface, making gusts feel stronger and more forceful. Storms might creep rather than sprint, pressing through valleys and plains with slow strength instead of racing across landscapes the way some storms do on Earth. Color in the sky would shift through the day in ways that feel known, yet not quite the same. Sunrise could begin in rich amber tones, spreading through the sky in long, smooth gradients, as if layers of warm light settle into the atmosphere. Even midday might carry a faint gold shimmer, breaking only when clouds clear enough to reveal a bright, steady star. Without strong ultraviolet scattering, blues might seem slightly deeper or softer depending on atmospheric makeup. And when evening comes, the world may lean heavily toward bronze and copper light, painting mountains, plains, and oceans in long dramatic shadows. Seasonal cycles would depend on the planet's tilt and orbit. Kepler-452B takes slightly longer to circle its star, meaning seasons would last longer. Imagine a spring drawn out across many months, where new growth rises slowly in steady warmth, or a winter that does not rush but settles like a patient frost, holding the world in quiet stillness. These long seasons could shape climates in unique ways. Ecosystems would adapt not to quick changes, but to slow, steady shifts. Some regions might bloom in long, mild periods, while others face extended droughts or long, cold stretches. Gentle breezes could move like thick air currents, soft but heavy, brushing against surfaces with weight. Yet when storms rise, they would likely be stronger and longer lasting. Lightning may flicker inside thick clouds rather than strike outward as often. Thunder could roll deeper, the sound traveling through dense atmosphere like a drumbeat moving through a wall. Fog may cling to valleys for days, rising only when the sun warms the land enough to lift it. Sunlight filtered through thick atmosphere would feel diffused, especially during seasons of heavy clouds. Forests might live in softened light most of the year. Sunrise could arrive not with a sudden burst, but like a slow glow spreading across the sky, as though the star patiently pushes back the night. The night sky itself may appear slightly dimmer if the atmosphere is dense, with stars blurred by haze near the horizon but still bright overhead. The Milky Way would stretch across the heavens much like it does here, yet its texture might seem smoother or softer. Moons, if the planet has them, would change the sky further. A large moon would paint tidal rhythms in the atmosphere, shaping winds and ocean tides. Its glow could pierce clouds at times, shining through like a silver coin behind frosted glass. If multiple moons circle the planet, the sky at night could feel full, with phases overlapping and shifting patterns marking the months. Their pull might stir tides stronger than on Earth, feeding weather cycles and ocean currents that shape seasons and growth. Weather on mountain ranges would hold special drama. Thick air climbing tall peaks would cool quickly, creating snowfall and sharp winds that cut down slopes in sudden bursts. Peaks could hide behind clouds much of the time, wearing caps of mist and ice that stay in place for long stretches. Valleys might be more humid, holding pockets of still air where dew gathers each morning. Plains may face wide storm fronts that crawl for days, soaking land until water pools in shallow basins before slowly sinking back into soil. Hurricanes could form differently. Warm water feeding dense atmosphere may give rise to vast rotating systems, but their height would be lower, spreading them wider rather than stacking them tall. These storms could drift across seas like slow-moving whirlpools of cloud and rain, carving patterns into waves and stirring deep water currents. On coasts, waves might hit harder because gravity pulls them down faster and pushes them back with more strength. Beaches could shape themselves differently, sand held tighter or washed away quicker depending on weather cycles. If deserts exist, heat trapped by thick air could make them feel intense, like giant ovens under a steady star. Wind could move sand in heavy sheets, sculpting low dunes that hold firm under weight. Dust storms might rise but stay low, sweeping across ground like rolling blankets rather than tall pillars swirling into the sky. During rare rains, water may rush fast through dry ground, carving deep channels before soaking in. Conversely, in colder regions, snow would fall faster and pack tighter. Ice might form in denser layers, building heavy sheets instead of airy crystals. Winter skies could hang low and grey for long stretches, light spreading wide but staying faint. Frozen lakes would sit under heavy lids of ice, and rivers would freeze deeper, their flow slowed by pressure. If humans evolved there instead of Earth, if humans had not risen on Earth, but instead on Kepler-452B, their bodies would tell the story of the world beneath them. Over many generations, natural selection would shape forms suited to this steady downward pull. Bodies would likely grow shorter and more compact, built to conserve energy and resist strain. Legs may be thicker, with dense bones and powerful joints. Spines would curve gently with strong support tissues around them. Not delicate, but firm, like the trunk of a tree that grew in constant wind. Hands might be wider, and fingers could be stronger, not from tools or work, but simply because daily life demands more strength to lift, to climb, to move across uneven ground. Movements would appear slower to us, not because thinking is slow, but because rushing costs more energy. Each jump, each run, each lift would burn more calories and strain more muscle than on Earth. The face may change subtly too. Breathing heavier air and dealing with a thicker atmosphere could give wider chests and stronger breathing muscles. Noses might be shorter and broader if moist air dominates, or longer and narrower if dryness shapes airways. Eyes may adjust to the slightly warmer light. Not dramatic changes, but subtle shifts. Lids that protect well against brightness. Pupils that manage long hours of gentle gold light. Skin tones would depend not only on sunlight strength, but on cloud cover and atmospheric thickness. With steady sun and long seasons, darker tones may evolve to protect from long-term radiation exposure. But if clouds often soften the light, there might be a range of tones across regions, just as on Earth. Hair could grow thicker to shield the scalp, or thinner in warm lowland areas where heat lingers. Nothing would be uniform. Nature rarely paints all beings the same way. Children on such a world might learn movement like careful hikers. Crawling, standing and walking would take more time, because lifting their own weight is harder. The first steps would be careful, like testing the planet's trust. Over time, muscles would form dense and efficient systems. Strength would not be a hobby or a sport. It would simply be the price of living. Feet would adapt to constant pressure, bones and arches sturdier, tendons thicker, toes spread slightly wider for balance. Each footfall would feel heavy at first to someone from Earth, yet to those born there, it would feel natural. Their pace may be measured and even conserving energy. Running, if done often, would look more like powerful bursts than endless jogging. Sit and rest moments may be more common simply because the body asks for them. Diet would shape evolution as well. Higher gravity burns more calories, but food supplies may not always keep up, especially if plant growth follows slow rhythms tied to long seasons. This would reward metabolism that knows how to ration energy. Bodies may store fat more efficiently, but also build muscle with ease, since muscle is needed for survival. Eating patterns could be steady and balanced, not feast or famine if food ecosystems are stable. Slow, patient gathering or farming might be common behavior over long evolutionary scales, but here we stay with biology, not culture. What matters is that energy use would be watched by nature like a careful accountant. Waste would not be forgiven easily. Their hearts would grow strong, but not oversized. Instead, walls of the heart might thicken slightly to push blood more forcefully against gravity. Blood vessels in the legs would form tight valves and tougher walls to stop pooling. Circulation would be a quiet battle against the world's pull. Yet bodies would master it, the same way plants master wind. Pressure and force would not weaken them, they would shape them. Bones would be dense, maybe heavier, with wide joint surfaces to spread force. This might make their skeletons seem heavier than ours. If someone from Earth tried to stand beside them, they might appear shorter but sturdier, like a mountain goat compared to a deer. A thicker atmosphere can carry sound farther and muffle sharp noises. Ears might tune better to softer sounds, able to catch gentle rustles in thick air. Eyes could learn to see through haze or catch motion in golden light. Touch may grow more sensitive in hands and feet because navigating uneven ground requires careful feedback. When every action costs more effort, thought tends to become deliberate. Life here would reward patience, planning, and quiet strength. Quick reactions still matter, but quick choices without thought would waste energy. People shaped by such evolution might value calmness, steady decision-making, and endurance. On Earth we know fast shifts, short winters, quick springs, sudden heat. On Kepler-452B, a season might feel like a slow tide. Minds shaped in such rhythms could think in longer stretches of time. Hope may not aim for tomorrow, but for months ahead. Worries may come not in sudden spikes, but in slow waves. A steady world makes steady minds. Harsh storms and heavy rainfall would teach respect for shelter and safe ground. Courage would not mean charging forward, but holding strong against the world's weight. Children growing up here might learn early how to move carefully, how to brace when wind presses hard, how to listen to the slow stories the land tells. Curiosity would still bloom, because curiosity is not born only from light worlds or easy lives. It comes from the need to understand surroundings. Observing changes in long seasons would teach attention to detail. Watching clouds shift slowly would train the eye to notice small patterns. Minds would grow sharp, but with patience rather than rush. Communication styles might lean toward calm speech, because air moves sound differently, and loud bursts of energy waste strength. Listening would hold high value. Silence might not feel empty. It might feel like breathing space for thought. Games would use strength and balance more than jumping or racing. Climbing low slopes, lifting stones, walking beams, learning how to manage weight and movement would prepare bodies quietly. Falls would hurt more. Gravity unforgiving. So evolution would reward carefulness, not recklessness. Sleep patterns might lengthen slightly as energy saves overnight. Muscles would rest with deeper need. Morning waking would feel like rising from a heavy blanket of gravity, but the body would adapt and move with steady force once warmed. All of this paints a picture not of strange creatures, but of humans, still recognizable in thought and wonder, just molded by extra weight and long light. Their faces might show calm strength, their steps sure and grounded, their voices steady. They would not see themselves as unusual. They would simply be right for their world, just as we are right for ours. Daily life on a slightly bigger, older Earth twin. Daily life on a world like Kepler-452b would move with a steady rhythm, shaped by gravity, light, and long seasons. Work still gets done, meals still get cooked, homes still rise from the ground, but all of it happens with a measured pace that respects the weight of the world. Morning begins quietly. The sun here is not harsh at dawn. It rises in a warm gold arc that spreads slowly over land and water. Muscles warm up before movement. Houses are built low and firm, spread wide rather than tall, because a taller home means more weight to support and more strain on materials. Thick beams angled inward handle pressure better. Foundations run deep, not only to anchor buildings against storms, but to carry the burden of heavier structures. Walls might be packed earth or stone mixed with fibers, materials that handle compression well. Walking paths are smooth and wide. Streets curve gently to avoid steep changes in height, because climbing a hill here feels like carrying groceries up a flight of stairs on Earth. People may lean forward a bit when they walk, as a natural stance for balance. Handrails follow slopes. Stairs are fewer, ramps more common. Shoes have thick soles to soften impact and spread weight. A long stroll here means something, like a workout and a journey at once. Farming would be a daily anchor, not just a task, but a relationship with soil. Soil under heavier rain and stronger storm bursts needs protection. Farmers lay wide terraces along hillsides, each one reinforced by roots, stones, and woven plant barriers. Crops are planted in layered beds to resist runoff and hold nutrients. Water channels run low and narrow, controlled by small gates that adjust flow. Irrigation is slow and steady. Sudden floods could rip seedlings from the earth. Seeds with thicker hulls and deeper first roots thrive best. Farmers walk fields with a patient step, checking leaves for sun stress, watching how dew gathers on thick air mornings. They know that a tired arm or careless lift wastes precious strength. Tools have wide handles for firm grips, and blades curve like claws to work into denser soil. In fields, plants stand sturdier, with firm stalks and leaves shaped to resist droop. Workers tend them with careful hands, easing weight off delicate stems. Harvesting requires planning. Heavy baskets rest on low sleds, or simple wheeled boards that drag across dirt rather than being lifted on backs. Sometimes animals do the pulling, but many times, slow human strength handles it. Inside homes, furniture is stout. Chairs have strong legs, beds sit low, shelves hug walls. Floors feel cool and steady. Windows are thick to withstand storms and pressure changes. Outside, roofs slope gradually to let rain slide instead of slam. When storms come, they come with force. Heavy air carries thunder deep, like a drum echoing in a stone room. Wind presses harder on bodies, so movement during storms stays indoors or close to ground shelters. People know to brace themselves when gusts arrive, bending knees slightly to stay grounded. Travel between towns does happen, but far trips take planning. Paths stretch across valleys and plateaus rather than climbing steep ridges. Wagons have wide wheels to spread load. Beasts of burden, if they exist here, move slow with thick legs and calm steps. Bridges sit low to water, anchored heavy with stone and thick fiber ropes. Travelers rest often. They drink slowly, saving energy. A journey that takes a day on Earth might take 2 or 3 here. Exploration feels like a blend of adventure and endurance. The world invites people to see its forests, rivers, and wide plains, but it also reminds them to prepare. Backpacks sit closer to the body with broad straps. Water skins are larger because heat from an older sun lingers in ground and stone long after sunset. Trail markers stand thick like pillars. When explorers walk, they place sticks underfoot to test ground softness, especially near riverbeds where heavier rain may have softened earth. Rest spots are built into trails. Simple stone benches shaded by wide-leaf trees. In towns, markets open when light is high. Sellers do not shout. Voices stay low and warm, and gestures speak as loudly as words. Goods rest close to the ground on wide tables. Baskets brim with grains, fruits, and hardy vegetables that grew slow and steady. A sack of grain feels heavier here, so buyers carry with both hands or place goods in rolling trays. People talk as they move, not fast chatter, but long, thoughtful exchanges. They share news of weather patterns, soil moisture, and crop timing. Knowledge of land is not a hobby. It is survival and community. Cooking uses steady heat, often from stoves that burn dense fuel bricks shaped from plant matter and minerals. Fire burns slow and strong, with heavy smoke that disperses through wide chimneys. Meals are hearty because bodies need dense energy. Grains, roots, slow-grown fruits, and thick greens fill plates. Evening brings longer twilight. The star cools on the horizon with a deep amber glow. People breathe easy after work, stretching sore arms and legs like living tuning forks vibrating down from effort. Toys for children are sturdy blocks, ropes and climbing frames low to the ground. Laughter sounds full in heavy air. Lanterns glow with soft light. Families gather on low cushions. At night, rest is fuel. Beds are firm to support weight. Dreams come slow and deep after days of steady effort. Outside, insects hum in thick air, and trees rustle with leaves built to handle wind. Distant storms flicker on horizons like ancient fire. The trouble with gravity. Leaving Kepler-452B by rocket. Getting off a world like Kepler-452B would not be simple. On Earth, rockets already push technology to its limits, fighting gravity with fire and steel. Now, imagine trying to rise from a planet where gravity holds you even tighter, like a firm hand on your shoulder that does not want you to stand up. The air might be thicker, the pull stronger, and every step upward would take more power. Spaceflight here would feel like wrestling with the planet itself. Engineers would begin with the same basic laws that guide our rockets. A ship must burn fuel to push downward, and that reaction lifts it upward. But if escape velocity on this planet is higher, the rocket must burn much longer and much harder. Escape velocity is the speed needed to break free from a world's pull. On Earth, it is about 11 kilometers per second. On a heavier world, it could be a few kilometers per second more. That number sounds small at first, like adding a few steps to a staircase. In truth, each extra unit demands far more fuel, because pushing a rocket a little faster means fighting a force that grows stronger with every kilogram of added weight. So rockets on Kepler-452B would need huge fuel tanks, larger engines, and stronger frames. But more fuel means more weight, and more weight means more power needed to lift it. A loop forms, the same one engineers face on Earth, but more intense. The best metals and the toughest engine designs might approach their limits. Pipes carrying fuel would need thicker walls to withstand pressure. Tanks would bulge with the strain of storing such large volumes. Every bolt and weld would be stressed by both gravity and vibration. Launch pads here would not look light or graceful. They would be carved deep into bedrock or built from dense stone and reinforced alloys. Towers might squat low and wide instead of stretching into the sky. The rocket itself would rest like a giant coiled muscle, heavy and tense, waiting for ignition. On launch day, flame would pour out in broad sheets instead of narrow streams, because the engines would burn at extreme power right from the start. The roar would press against the ground and air like a rolling shockwave. Dust would not simply puff, it would slam upward and then crash back down in thick clouds. The rocket would climb slower at first, struggling to break free, rising like someone lifting themselves from deep water. On Earth, rockets lean into the sky smoothly after clearing the tower. Here, the tilt might come later, once engines prove they can carry the load. Pilots, if any, would feel crushing force on their chests as the rocket pushes against gravity. Even robots and instruments inside would need extra support frames to survive the stress. Fuel chemistry would also matter more. On a world like this, scientists might lean toward fuels with more punch per drop, combinations that burn hotter and faster. But power brings risk. Stronger fuels mean greater danger in storage and during launch. Safety crews would train in thicker suits, with reinforced vehicles ready to respond if tanks rupture or lines fail. Protective zones around launch sites would stretch farther, not because flame travels farther, but because shock waves in higher gravity land harder and travel differently through air and soil. If space programs here existed early in history, progress would move slower. Each rocket test would cost more, fail harder, and demand more lessons. But determined minds would still try. Curiosity is stubborn. It does not give up simply because the ground holds tighter. Engineers would study lighter materials, even if those materials press harder under their own mass. They might build composite skins and fiber-wrapped tanks that help share weight. They could use aerodynamic shapes that cut through thick lower air before rising into thinner layers if the planet has similar atmospheric structure. Everything would hinge on squeezing performance from each design choice. Some ideas that Earth has tested on paper might become real here. Launch pads placed on tall plateaus could lower air resistance in the first seconds. Maglev rail systems could give rockets a boost before engines fire, reducing fuel needs at liftoff. Staged rockets would be mandatory, with each layer peeling off like petals, shedding weight as they burn through fuel. Each stage would be heavier and stronger than its Earth version, yet shaped with careful curves to spread stress. Even with all this effort, launches might not be frequent. They would feel like long-awaited events, with whole communities following countdowns and watching trails of flame streak skyward. Children might learn early that spaceflight is not a casual dream, but a heavy challenge. Posters in classrooms might show diagrams explaining gravity wells and escape curves, helping young minds understand why their world asks for more strength than Earth does. But higher gravity does not mean defeat. Humanity has pushed against limits before. It built ships to cross oceans, rails to cross continents, and rockets to leave Earth. The same spirit would exist here, shaped by effort, but not crushed by it. Engineers would keep solving problems one by one. They would test smaller boosters first, then larger ones. They would model fuel flows, engine thrust curves, and structural stress. They would use wind tunnels, vibration chambers, and pressure tests to guard against failure. When a rocket finally reaches orbit, the victory would feel deep and earned. The craft would glide above the thick pull, coasting where gravity weakens and the sky turns black. Down below, the planet would haze under clouds and golden light, looking peaceful but heavy, like a marble resting in a giant's hand. The engineers would know each launch is not only a step into space, but a reminder of how tightly gravity once held them. If space stations circle this world, they would become symbols of persistence. They would not be simple labs, but monuments to the strength required to rise. Astronauts here, whether human or human-like, would train harder, building bodies to endure intense G-forces at launch. Capsules might need shock-resistant seats, deep harnesses, and stronger frames to handle the climb. Every return to the surface would also demand control. Landing on a heavier world takes more thrust and more precision. Parachutes alone might not slow a craft enough. Retro rockets would fire hard, kicking up dust and leaving scorch marks on landing pads. Pilots would brace for the moment wheels or legs touch ground, feeling the planet pull them home with a firm, undeniable grip. Gravity, silent and steady, would stand as both a challenger and a teacher. And each time someone breaks free of it, even for a short orbit, the moment would echo through history, marking a victory carved from physics, sweat, and patience. Tools we need to truly see the planet. To see a world across the vast arc of space sounds simple. Point a telescope, collect light, look closer, but the universe does not give away details so easily. Light stretches, scatters, blends together. Stars shine like blowtorches in the night, drowning out anything near them. And planets, even big ones like Kepler-452B, try their best to hide in that brightness. They are tiny next to their suns, and the light they reflect is faint, like dust floating in a beam from a window. So even though we know Kepler-452b is there, the truth is that right now it is more mystery than world. The problem begins with distance. Kepler-452b sits about 1,400 light-years away. That number feels almost unreal. If you had a ship that could travel as fast as the fastest spacecraft humans ever made, the trip would take millions of years. Light, the fastest thing in existence, needs 14 centuries to reach us. By the time those photons arrive, they carry only the faintest whisper from that far-off place. They are stretched thin by distance, like old photographs left in the sun. So when they reach our telescopes, they arrive mixed with light from other stars, dust, and the general glow of the universe. Even with a telescope as powerful as the James Webb Space Telescope, the planet is still a point. Not a circle, not a glowing marble, just a single pixel in the ocean of the sky. A planet thousands of kilometers across shrinks to something smaller than a grain of sand seen from across a football field. If we try to look harder, the starlight gets in the way. The star Kepler-452 shines so brightly that it washes out details around it. Imagine trying to spot a firefly sitting on the rim of a lighthouse beam. The light you want is there, but lost in glare. Telescopes on Earth have their own trouble. The atmosphere moves and bends light, like heat waves above a road. Stars twinkle because of this. Planets blur. We use adaptive optics to correct some of it, changing the shape of mirrors in real time. But even then, Earth's atmosphere is like a restless ocean of air. It moves faster than our machines can fix. So for the best clarity, we need telescopes in space. But even in space, size limits vision. A telescope's power depends partly on the width of its mirror. Bigger mirror, finer detail. Earth, with its largest ground-based telescopes, can see some features on planets closer to us. But Kepler, Kepler-452b is too far. To see its surface directly, we would need a telescope far bigger than anything ever launched, something with a mirror kilometers wide, not meters. And building, launching and deploying such a machine is far beyond our present reach. Our rockets cannot lift it, and our systems could not unfold it. There are clever tricks scientists use to work around this. One idea is called a coronagraph, a device that blocks a star's light inside a telescope, like holding up your thumb to block the sun. When it works well, the planet next to the star can be seen better. But coronagraphs are delicate and hard to build. They need perfect precision. Even one small vibration can ruin the image. Another idea is a starshade, a thin, giant shadow-casting shape that would float far away from a telescope in space. It would block the star's light before it even enters the telescope, leaving the planet visible. But controlling two spacecraft across tens of thousands of kilometers, keeping them aligned perfectly, is a huge engineering challenge. Resolution, the sharpness of a view, is not only about power, it is also about noise. Stars flicker, dust glows, galaxies hum in the background. All this light mixes together by the time it reaches us. Astronomers build tools to filter and separate signals, breaking light into colors and studying their patterns. This helps us measure gases in the atmosphere of other planets. We look for oxygen, methane, carbon dioxide, water vapor. Even though we cannot see oceans or forests, the air might tell us if they exist. Webb and future telescopes can do this for planets around closer stars. For Kepler-452b, the distance still challenges us. Its signal blends too much. We need sharper tools, cleaner instruments, and better ways to block starlight. Imagine a future telescope the size of a city, floating in space like a silver moon. Its instruments so cold they hum at the edge of silence. Its mirrors polished beyond the smoothness of any surface humans have ever made. With a machine like that, Kepler-452b might bloom into view. We could see continents, maybe clouds curling over a mountain range, oceans shining like polished stone. But that dream still sits in the far future. Some researchers imagine using gravitational lensing. Space itself bends light, and massive objects, like stars or black holes, act like natural telescopes. If we could position a spacecraft at the right place, far away from the sun, we might use the sun's gravity to magnify the image of a distant planet. It would take decades to send a probe there. And even if we reached it, aligning everything correctly would be one of the hardest feats in science. Yet human curiosity does not stop at difficulty. Every great telescope we built once sounded impossible. People once doubted we could launch Hubble. They doubted we could build mirrors for Webb that fold like origami. And yet in orbit, those machines now gather light from places we never saw before. Each time we reach further, the universe answers back. We find more worlds, more stars, more reasons to keep going. The universe does not rush. Light travels at its own pace, and discovery grows step by step. Our tools sharpen, our methods improve, and our dreams stretch a little farther each year. Somewhere ahead lies a day when we will stare at Kepler-452b not as a number, not as a distant point, but as a world. A world with textures and shadows and weather and land. A world that once lived only in imagination, brought into sight by machines built with steady hands and stubborn hope. Future telescopes, and the dream of a direct image. We already have telescopes that can spot planets around other stars. We can measure their orbits and read some of the gases in their skies. But to look at one as clearly as we look at a distant mountain on Earth, we need machines beyond anything we have built before. Machines that change how we see the universe. The first steps are already planned. Missions like the Nancy Grace Roman Space Telescope will open new doors. Roman will carry a coronagraph, one of the most advanced ever made. It will try to block starlight so we can see the dim glow of planets around them. It may not reveal clear surfaces, and Kepler-452b is too far for it to sharpen much, but Roman will prove ideas in space. Every test done there teaches us how to build better systems later. It is a path of progress. Prove the concept, learn from mistakes, build again. Then there are starshades. In design, their shape often looks like a giant flower when drawn, with petal edges to soften the way light bends around it. This idea has been studied for years. Engineers know what size it likely needs to be, how far it must sit from a telescope, and how sensitive its alignment must stay. The numbers are intense. It might need to sit tens of thousands of kilometers away. It must move slowly and hold its position almost perfectly. But these challenges do not stop the planning. They only sharpen the questions. What propulsion system works best? How do we fold something hundreds of feet wide for launch? How do we keep sunlight and heat from warping its shape? These are hard problems, but not impossible ones. Another future dream is building truly giant mirrors in space. On Earth, mirrors for telescopes are limited by the size of rockets. Webb needed mirrors that fold like puzzle pieces. It was one of the most difficult engineering tasks ever done in space, but future designs stretch far beyond that. Imagine a telescope with a mirror tens or even hundreds of meters across, something like a vast metal flower opening in orbit, each petal a piece of polished surface catching starlight. With mirrors that big, faraway planets would not be points anymore. They would start to gain shape. Not clear like a photograph from a plane window, but enough to see oceans, clouds, and dark patches that might be forests or land. These mirror designs come in different forms. Some may use solid panels, unfolding one by one. Others might use thin film mirrors stretched over frames, light as foil but held smooth by tension. Some engineers think about using robots to build mirrors in space, placing segments like tiles until a vast eye grows in orbit. That removes launch size limits. A robot arm could place 1,000 pieces if needed. It would take time and precision and patience. But a machine like that could change astronomy forever. There are even more ambitious ideas. Interferometry in space, where several small telescopes fly in formation and combine their signals, acting like one giant lens. The distance between them becomes part of the viewing power. With enough spacecraft working together, we could build a virtual telescope the size of a city, or even bigger. They would not touch. They would drift and adjust, linked only by computers and light beams. The concept exists in early experiments already. We have done it with radio telescopes across Earth. We have tested small formation flying in orbit. Putting it all together is a challenge, but not a fantasy. The idea of using the sun itself as a lens sits at the edge of human imagination, yet the physics is sound. Far beyond Neptune, at a point where the sun's gravity bends light just right, a spacecraft could sit and catch magnified images of a distant world. If it pointed at Kepler-452B and waited for the right alignment, it might see details we can hardly believe: continents, seas, even weather patterns. But to reach that spot requires decades of travel. The craft would need to power itself for a long time, communicate across unimaginable distance, and align with precision greater than anything we have attempted. It is the kind of mission a generation begins, and the next generation watches unfold. Each idea has hurdles. Big mirrors are heavy, delicate surfaces bend. Formation flying takes fuel and perfect control. Starshades require exact timing. Gravitational lensing demands patience and distance. But history shows what happens when we follow long, hard paths in science. We once thought radio waves could not cross an ocean. We once believed rockets could not break free from Earth. We once thought planets around other stars were only guesswork. Each barrier fell one by one, under hands that built, tested, failed, and tried again. The roadmap to a true image of Kepler-452b will likely pass through several missions. First, we refine coronagraphs. We practice with starshades on smaller scales. We send telescopes with greater diameter to orbit, maybe a 6-meter mirror, then a 12-meter, then bigger still. Step by step, our vision sharpens. Some missions will be approved, some delayed, some cancelled. Progress rarely moves in a straight line, but the direction of the journey stays clear, towards seeing other worlds as worlds, not dots. What would that moment feel like? A screen showing something round, something living under a star far from home. Not an artist's guess, not a simulation, but light gathered straight from alien oceans or mountains. For scientists, it will be a breath held for decades finally let go. For the public, it may feel like looking into a window across the galaxy, a reminder that planets are not rare and Earth is not the only stage nature builds. To look at another Earth-like world with true clarity would change how we see our own. It would remind us that worlds are fragile, that they can be lost or thrive or remain quiet for eons. It would remind us that space is not empty, but rich with places waiting to be known, and that knowing takes patience, effort, and a bit of boldness. So even now, while Kepler-452b hides behind the shine of its star, the work continues. Engineers tune lasers that may guide future formation flying craft. Technicians polish mirrors to levels smoother than glass on a still pond. Scientists write code to filter noise from faint signals. High school students look through small telescopes and dream about the giant ones that will follow. Every piece fits into the long story of learning how to see across the stars. The universe is out there, calm and wide and waiting. And somewhere in that distance, a blue-green world circles a warm sun, its details blurred by distance, but not forever. Future telescopes will grow, starshades will unfurl, and mirrors will stretch open like wings. Someday, the first clear picture of a distant Earth will appear, and the quiet glow of that moment will reach everyone who has ever looked up and wondered. Spectral fingerprints, searching for air, clouds, and life signs. To find spectral fingerprints, astronomers first take the starlight alone. They measure its spectrum with the planet hidden or behind the star. That gives them a clean before image of the star's light. Then they wait for the planet to pass in front of the star. As it crosses, a tiny fraction of starlight filters through the edge of the planet's atmosphere. Even if the atmosphere is thin, a sliver of it sits between us and the star. In that brief moment, the starlight is changed. Now the spectrum holds extra dips where gas molecules absorbed certain colors. The difference between the two spectra, with and without the planet, is where the secrets hide. It is a subtraction game. It is also incredibly precise. A dip might be less than 1 part in 10,000. For small molecules like oxygen or methane, the signal might be so faint that only the most sensitive instruments can pick it up, and even then, only if the data is stacked from many transits. Sometimes astronomers wait years for enough passes. Sometimes noise from a telescope, a sensor glitch, or interference from Earth's own atmosphere has to be removed, pixel by pixel, until the pattern becomes clear. Each gas has its own spectral signature. Oxygen absorbs near 760 nanometers. Methane leaves marks near 1.6 microns. Water vapor spreads a series of bands across the infrared. Carbon dioxide, ozone, and nitrogen also have distinct fingerprints. When these lines appear together in the right balance, they can point towards specific surface and atmospheric processes. Water vapor hints at a water cycle. Carbon dioxide helps trap heat. Oxygen alone is not proof of life, because sunlight can split carbon dioxide and build oxygen in thin atmospheres. But oxygen mixed with methane in steady amounts is harder to explain without biology. On Earth, microbes create methane faster than sunlight destroys it. Plants replace oxygen faster than it reacts with rocks or burns in fires. Life holds these two gases in a controlled imbalance. If a distant world shows a similar imbalance, it becomes a major point of interest. Kepler-452b gives us a good target for such work because its size and orbit make it possible that it has an atmosphere thick enough to leave readable signals. A rocky world with no air would show almost nothing during a transit. A planet covered in haze like Titan might blur the lines, hiding deeper gases. A world with dense clouds like Venus could scatter so much light that chemical marks are muted. Each case leaves a different spectral texture. Even cloud height matters. High clouds block the signature of gases below, while low clouds might still let the starlight pass through upper layers. That means learning about clouds is not just a question of weather. It is an extra puzzle piece tied to chemistry and surface conditions. To measure tiny shifts like this, telescopes need stable mirrors, ultra-quiet detectors, and long observing windows. Instruments must be cooled so heat from the telescope itself does not flood the sensors. A small vibration can smear lines. A drifting orbit can slightly change angles and warp readings. Data pipelines must correct for scattered light, cosmic rays hitting the detector, Earth's atmosphere if the telescope is on the ground, and even tiny temperature swings in the hardware. What ends up in a published paper often comes from thousands of hours of cleaning, calibration, and rechecking. Another way to study spectra comes when the planet moves behind the star. As it disappears, we briefly lose the light reflected from the planet. This lets scientists isolate how much of the star's light bounced off the planet and study it. If the atmosphere has clouds, their reflectivity can create a certain brightness curve. If the surface has oceans or ice, the spectrum might show glints or reflectance shapes that do not match bare rock. Water, especially, has a very recognizable infrared absorption pattern. A strong signal would not prove oceans, but it would raise the odds. Infrared instruments also let us measure heat emissions from the planet itself. A rocky surface radiates heat differently than thick clouds or gas layers. If the planet's night side remains warm, that means heat is being moved around the atmosphere. If the day side is much hotter, the air may be thin. Temperature curves like this help build climate models. Even without seeing a map, you can estimate wind strength, cloud altitude, and how fast heat cycles across the globe. Chemical pairs matter as much as individual gases. Nitrogen plus oxygen suggests Earth-like air pressure. Carbon dioxide with water vapor and faint methane might point toward active heat balance. If we saw sulfur dioxide or weird nitrogen oxides in large amounts, we might suspect volcanoes or chemical reactions in the upper atmosphere. These details do not hand us a direct answer. They narrow down possibilities. They turn questions like, is there life, into, does this look more like a living atmosphere or a geological one? False positives remain a constant risk. For example, a planet with a runaway greenhouse could produce oxygen by breaking apart water molecules and losing the hydrogen to space. The oxygen left behind would be a ghost signal, not a breath of life. A quiet frozen world could show no oxygen at all, even if it once had life, simply because it is trapped under ice or lost its atmosphere. Scientists treat each line with caution. They study star activity too. A very active star can break molecules and create spectral noise. Kepler-452 star is calm, which makes things easier, but time still works against us. If the planet is losing water slowly, its chemical balance may be shifting, and we must interpret signals in light of an aging world. If one day we collect a spectrum that shows strong water vapor bands, a stable trace of oxygen, a hint of methane and temperature curves that point to clouds and weather, it will not instantly prove life. But it will make scientists sit very still, check the data again and again, and then begin cautious debate. Light would not just be light anymore. It would be a record of chemistry shaped by something dynamic at the surface, something that breathes, changes, and leaves marks in the air. Spectroscopy will not give us aliens waving or landscapes glowing under an older sun. It will give us numbers, lines, and curves. Yet in those lines, we will find the closest thing to a conversation with a far world. It lets us reach across light years and test the air of a planet we can barely see. It turns starlight into evidence and chemistry into a clue. And it lets us look at a quiet dot in the sky and begin to understand whether it is a silent rock or a living world. How long until we know for sure? If someone asked how long it will take before we can know for sure what Kepler-452B looks like, there would be no single answer. The truth depends on how quickly technology improves and how funding flows. What we can say, though, is that direct knowledge, real images, real atmospheric readings, and reliable surface data will not come soon. The distance of over 1,000 light-years sets a hard wall around our reach. So the timeline is tied to what our telescopes and instruments can do from here, not what we can send there. Today, even our most powerful space telescope cannot see Kepler-452b directly. For perspective, the star's light is about 10 billion times brighter than the planet's reflection. JWST can detect some large exoplanets in closer systems, but Kepler-452b is far smaller, dimmer, and farther away. What we have instead are indirect measurements. To go beyond that, we need new kinds of instruments. Over the next 2 decades, several large telescopes are planned that could slowly bridge the gap. The first wave will come from the ground. The extremely large telescope in Chile, the 30-meter telescope in Hawaii, and the giant Magellan telescope in Chile. Each of these will use mirrors many times wider than any telescope we have now. With that larger collecting area, they will catch more light and separate faint signals more sharply. These telescopes are expected to begin operation sometime between the late 2020s and the mid-2030s, depending on funding and construction progress. Still, even they will not show us the face of Kepler-452b. At best, they could study its star's light with higher precision and detect more subtle wobbles, helping refine the planet's mass and orbit. They could also test spectroscopy on nearer Earth-sized worlds, proving the techniques we will one day apply to distant ones like Kepler-452b. In other words, the next 10 to 20 years will be training years. Years of testing tools on closer examples before using them to decode the faraway ones. The next step after that would be telescopes in space with mirrors larger than JWSTs, designed specifically for imaging exoplanets. NASA and other agencies have proposed several missions, each more ambitious than the last. One of them is the Habitable Worlds Observatory, sometimes called HWO. It is planned as a follow-up to JWST, possibly launching in the 2040s. It would use a combination of a large segmented mirror and a starshade. The starshade idea is elegant but technically demanding. The 2 spacecraft must communicate and move together smoothly, which is like 2 dancers performing in the dark, separated by hundreds of miles, both guided only by radio signals. Engineers have tested miniature versions of this system in laboratories, but it has never yet been done in space. Even if the technology works, the first full-scale test would probably target closer, brighter systems, not one as far as Kepler-452b. Another concept, LUVOIR, or the Large UV Optical Infrared Surveyor, was once proposed as an enormous space telescope with a mirror up to 15 meters wide, about 3 times larger than JWST's. A mirror that large could, in theory, separate the light of Earth-sized planets from their stars in nearby systems and perform detailed spectroscopy on their atmospheres. But LUVOIR's projected cost and complexity put it decades away, if it is ever built. Even if launched in the 2050s or 2060s, its reach would likely stop at a few hundred light-years. That means Kepler-452b would remain just out of range for direct imaging. We might still use it to confirm worlds similar to it, but much closer, teaching us indirectly what Kepler-452b could be like. To reach a planet that distant with a sharp enough image, we might need telescopes not limited by single mirrors. In theory, a formation of telescopes spread across thousands of kilometers could see the surface of an exoplanet, like Kepler-452b, in remarkable detail. In practice, though, this requires a level of coordination and data merging that no current technology can achieve. The phase alignment of light waves must be perfect, and the data streams must be synced with timing accuracy far beyond today's limits. Some space agencies have proposed early experiments with small versions of such arrays, but these remain on paper or at the simulation stage. If progress continues, maybe by the second half of this century, around the year 2080 or later, we might see the first usable results from such techniques. There are also smaller but clever approaches being studied. Some scientists are testing coronagraphs that sit inside telescopes, blocking a star's glare without needing a separate shade. Others are designing new light sensors that can detect single photons with lower noise, making it easier to pull faint planetary light out of a bright background. Machine learning is being trained to spot patterns that traditional analysis might miss, teasing out weak signals that hide in data. These methods will help us study many planets. but distance remains the immovable obstacle. The farther away a planet is, the dimmer its reflected light becomes. Every doubling of distance makes it 4 times harder to see. For Kepler-452b, which is thousands of trillions of kilometers away, that difference is enormous. If we imagine a future when humans build solar system-scale telescopes, structures floating far from Earth, maybe connected across millions of kilometers, we could start talking about real images of Kepler-452b. A telescope array positioned around the orbit of Earth or beyond could, in theory, combine light precisely enough to create planet-level resolution even for targets over 1,000 light-years away. But such projects belong to the far future, likely the 22nd century or beyond. They require stable space industries, long-term funding, and automated systems that can operate and self-repair for centuries. These are engineering dreams more than near-term goals. In more realistic terms, our first true spectral analysis of Kepler-452b's atmosphere could arrive in the second half of this century. By then, next-generation observatories could collect enough light, even faintly, to detect the chemical composition of its air. It will not give us images, but it could confirm whether the planet still holds water vapor or has lost it. It could tell us if carbon dioxide dominates or if some unexpected gas balance appears. That kind of result would count as knowing for sure in the scientific sense, because we will have reliable data on its air and climate. The waiting game is part of astronomy's nature. When Galileo looked at Jupiter's moons, he could not imagine a telescope in space measuring light from other stars. When Kepler's team found Kepler-452b in 2015, they knew they had no tool to study it directly, but they also knew that technology never stands still. Every generation builds sharper eyes. Every telescope becomes the stepping stone to the next. If history is any guide, within 50 to 70 years, we may have instruments that can measure the atmospheres of many Earth-sized exoplanets and compare them side by side. Kepler-452b, being one of the first known near twins of Earth, will likely remain a symbolic target, a world we use as a benchmark, even if we never see it clearly. By then, younger and closer planets found by future surveys may give us direct visual and chemical evidence of life, helping us understand what Kepler-452b might have been like without ever having to go there. So, how long until we know for sure? Realistically, a few human generations. Maybe the late 21st century for atmospheric details, and the 22nd for any direct image. The answers will come slowly, built photon by photon, through technology that does not yet exist. But the direction is clear. The story of Kepler-452b will move forward not through leaps, but through steady light, each telescope capturing a little more of it, until the world hidden there begins to take shape in our data. Could we ever travel there? If we tried to cross that gulf between us and Kepler-452b with today's technology, the limits would become clear very quickly. The fastest spacecraft humans have ever built is the Parker Solar Probe. It can travel at about 700,000 kilometers per hour at its peak speed when it dives close to the Sun. Even at that extraordinary pace, it would take more than 2 million years to reach Kepler-452b. That's not just beyond our lifetimes, it's beyond any continuity of civilization as we know it. No ship could last that long, and no system could sustain life or power across such a timescale. Even if we imagine a future craft moving much faster, the numbers remain crushing. Suppose a ship could travel at 1/10 the speed of light, an incredible velocity compared to anything human-made. At that rate, the trip would still take over 10,000 years. To move at even that fraction of light speed would require energy beyond anything we can currently generate. Accelerating a large spacecraft, even one just the size of a commercial airliner, to that speed would need roughly the total energy output of entire nations for years. It's not just a matter of propulsion design, but of raw physics. Every bit of mass that gains speed needs energy, and the energy required grows exponentially as you approach light speed. The challenge starts right at launch. Rockets on Earth work by carrying both their fuel and the oxidizer needed for combustion. But the faster you want to go, the more fuel you need, and the more fuel you need, the heavier the rocket becomes. This creates a spiral of diminishing returns. The rocket equation, discovered in the early 20th century, makes this clear. The ratio of fuel mass to payload mass increases dramatically with higher speeds. To reach even 1% of light speed, a chemical rocket would need to carry an impossible amount of propellant, hundreds or thousands of times its payload weight. This is why engineers and physicists have long looked beyond chemical propulsion. Ion engines, for example, use electricity to accelerate charged particles out the back of a spacecraft, creating thrust far more efficiently. NASA's Dawn mission used such an engine to travel between asteroids in our solar system. But while ion propulsion is extremely fuel efficient, its thrust is weak. It's like the steady push of a feather in a vacuum. Over long periods, that can build impressive speeds, but still not anywhere close to interstellar levels. At best, an ion-driven craft might reach a few hundred kilometers per second, still thousands of times too slow for a journey of light years. Some theorists have proposed nuclear propulsion as a next step. In the 1960s, Project Orion explored the idea of a spacecraft pushed forward by detonating small nuclear bombs behind it, using a massive plate to absorb and redirect the blasts. It would have been loud, heavy, and politically difficult. But in theory, such a ship could reach a few percent of light speed. That's still far short of what's needed for Kepler-452B, but it begins to approach interstellar capability. Even then, a trip would take thousands of years, and shielding a crew from radiation for that long remains unsolved. The project was abandoned before a prototype was ever built, leaving it as a bold footnote in the history of engineering ideas. Another nuclear-based design called a fusion drive might someday offer more hope. Fusion, the process that powers the sun, releases enormous energy from small amounts of fuel, such as hydrogen isotopes. If humans ever managed to control it efficiently, a fusion engine could continuously accelerate a spacecraft over long distances. The proposed Daedalus project, designed in the 1970s by the British Interplanetary Society, imagined a fusion-powered probe that could reach about 12% of light speed. It would still take around 9,000 years to reach Kepler-452B, but unlike earlier ideas, it didn't require refueling or impossible mass ratios. However, fusion itself remains an unsolved challenge even here on Earth. Every experiment so far has consumed more energy than it produced. Until that changes, fusion drives remain more concept than construction. In more recent decades, some scientists and entrepreneurs have turned to concepts that don't rely on carrying fuel at all. One promising idea is the light sail, essentially a thin, reflective sheet that can be pushed by light itself. Since light carries momentum, a powerful enough beam, such as a focused laser from Earth or the sun's natural radiation, could push a spacecraft forward. The Breakthrough Starshot project, proposed in 2016, builds on this principle. It suggests launching tiny gram-scale probes with powerful lasers, accelerating them to 20% of light speed. At that rate, they could reach Alpha Centauri, the nearest star system, within about 20 years. But even that ambitious concept would take over 5,000 years to reach Kepler-452B, and those small probes would only carry cameras and sensors, not people or large instruments. The deeper problem isn't just speed, it's scale. Sending even a small robotic probe to a distant system requires incredible precision in navigation, communication, and protection from interstellar dust. At 1/10 light speed, even a grain of sand could destroy a spacecraft on impact. The energy involved in such collisions would be catastrophic, like bullets made of vaporized metal striking at cosmic speed. Shielding would need to be extremely strong, yet lightweight, another contradiction that remains unresolved. If we imagine not just probes but crewed missions, the challenge grows exponentially. A human journey to Kepler-452b would need life support systems capable of lasting for thousands of years, or entire generations of travelers living and dying on board. That raises social, biological, and psychological questions as much as technological ones. How would such a crew maintain culture, purpose, and identity over dozens of generations? How would repairs be made or knowledge passed on? The idea of a generation ship has appeared in fiction, but even with perfect planning, the practical problems are immense. A small, closed environment would eventually face resource depletion, ecosystem collapse, or internal instability. So, if physical travel seems impossible now, the next question becomes whether we could send something non-physical, information perhaps. Even radio signals, which travel at the speed of light, would take over 1,000 years to arrive. A message sent today would reach Kepler-452B's orbit long after every person alive now was gone. Any reply would return another 1,000 years later. In cosmic terms, that's just a pause. In human terms, it's an eternity. Communication across that distance is as unreachable as travel itself. The reality is that we live in a universe both open and closed. Open because we can see and study distant worlds. Closed because we cannot touch them. Every time a telescope detects a planet like Kepler-452b, it expands our mental borders but reminds us of our physical limits. The energy needed to cross the gap is not just beyond our current reach. It may be beyond what any civilization could routinely manage without technologies that bend the laws of physics. Concepts like warp drives or wormholes often appear in speculation, but they rely on theoretical constructs, exotic matter, negative energy, that may not exist in usable form. Still, there's value in thinking about the limits. The same calculations that show we cannot travel to Kepler-452b today also point to what would be required to make it possible someday. Far more efficient propulsion, sustainable energy sources, and perhaps entirely new physics. Each step we take, each engine test, each telescope upgrade, edges us closer to understanding what might eventually bridge the light years. Right now, travel to Kepler-452b belongs to the realm of physics lessons. A ship could be launched today and the stars would shift, the continents would move, and even languages might vanish before it ever arrived. Yet, even knowing this, humans still look at that distant world and ask, could we go? The question itself is part of what drives exploration. It's less about the journey than the boundary. Each impossible distance becomes the next frontier to imagine. Someday, long after current technology has been replaced and our understanding of space has deepened beyond recognition, that question might change from could we ever to how soon can we? But for now, Kepler-452b remains where it has always been, far beyond our reach. What other fascinating planets would you like to travel to next? Sound off in the comments below, and if you enjoyed the video, consider leaving a like and subscribing. Thanks for watching.